A very good evening, one and all. The agenda for today is to cover artificial neural network and clustering techniques. So, in the first session, we're going to cover introduction to artificial neural network, and the second section we will see unsupervised learning, that is clustering. Right. So, let's start with artificial neural network. So in this session, we're going to discuss introduction to neural network and why do we need this artificial neural network, some motivating examples, forward propagation, backward propagation, and applications of this artificial neural network. Right. So this is the outline of this particular session. So what is this artificial neural network? So what is uh, uh, biological neural network? Our human brain consists of hundreds of neurons, and all of them are interconnected. Many of them are interconnected to each other. One neuron is connected to many other neurons, isn't it? So, our human brain consists of 100, around 80 million to 100 millions of neurons, right? So, they interconnection them to do certain things, certain work. Okay, so similarly, artificial neural network is an interconnected group of nodes inspired by the simplifications of neurons in the brain. Okay, so the origin of or the original goal of this artificial neural network is to mimic the human brain, to do tasks, to perform tasks that typically requires human intervention. Right, but the current attention is limited to performing specific tasks like visit recognition or character recognition or computer vision, speech recognition, machine translation, or social network filtering, or playing games, or medical diagnosis. So these are the individual tasks that varieties of tasks that the neural network can perform. Right. So it was started with the intention of creating a human-like intelligence, but the current intention is limited to performing specific tasks. Okay. So as I mentioned you, that human brain has 80 million to 100 millions of neurons connected together. Okay. And depending on where these neurons are located in the brain, okay, so they perform specific tasks. Okay, so say for example, some part of the brain is responsible for vision. Some part of the brain is responsible for hearing. Some part of the brain is interpreting the pain and touch. Okay, so some part is responsible for movement. Right. So, depending on where these neurons are located in our brain, they perform various activities. So, if I'm speaking to you, it means that some part of my brain is working. If you are listening to me, if you could listen to me, it means that some part of your brain is working. If you could react to my speech, then some part of your brain is working. So, like this, to perform various tasks, various parts of our brain is working. Right. So the neurons in that particular part are working. Right. But irrespective of where these neurons are located in the brain, they have got some common structure. Okay. So the neuron has all these neurons, irrespective of where they are located in our brain, they have got some common structure, some common parts. Okay. So this is how the neuron, the biological neuron, looks like. Irrespective of where they are located in the brain, the common structure is this. They've got some common parts like dendroids, cell body, synapses, axon. All these are the common parts that they have got. Right. So what is the functionality of the dendroid? What is the functionality of the cell body? And what is the functionality of the axon? And what is the functionality of the synapses? And how could we relate it to the artificial neuron? So that's what we're going to see in this slide. So dendroids are like inputs. They receive spiking signals from the other neurons. So the dendroids receive the spiking signals from the other neurons, right? So they receive input from the other neurons. So these are the dendroids. and width of the dendroid determines the weight associated with it. And this is a cell body, or we also call it as soma. Okay, so it receives this signals from the dendrites and integrate them. Okay, so if the resulting signal voltage is greater than certain threshold, then it passes that signal to this axon. Okay, so if you see, the dendrites are receiving these spiking signals and soma is integrating them. If the resulting signal's voltage is greater than certain threshold, it is passing that signal to this axon. So axon is a tail-like structure which plays an important role in carrying the signal generated by the soma. Okay, so it passes the signal to the synapses. Synapses play an important role in transferring the data from the axon to the dendrites of the next neuron. So synapses connect the axon of the last neuron with the dendrite of the next neuron. Okay, and again the process repeats. Dendrite receives signals from the other neurons, soma integrates them, and if the resulting signal's voltage is greater than certain threshold, it passes that to axon, and through axon it goes to the synapses. Synapses connects the axon of the last neuron with the dendrite of the next neuron. So this is how the information is communicated among the network of the biological neurons. And all these neurons together performing some functionality like vision or like hearing or like speaking or reacting, interpreting the pain and touch, right? So these are the various activities that group of neurons together doing, right? So when I'm speaking to you, we cannot, we don't know how many neurons in my brain are firing, okay, working together, right? So this is the brief overview of the biological neural network and biological neuron. Okay, so let us this to artificial neuron. So in the artificial neuron also we have the inputs. Inputs are x1 to xn. Okay, so you can imagine these edges as the dendrites which receives this input. And there is a weight associated with each one of these edges which determines the weight associated with that particular dendrite-like structure. Right? And this is a function where activation function we call it as, where that integration of the different inputs combined weighted inputs is happening, and if the resulting signal is greater than certain threshold, we say it is 1, otherwise it is 0. Okay, so we give the output, and this output is passed as the input for the next level neurons. So if you see, this is level 1, level 2, level 3, so on, level 4. At the level 1, we receive inputs and we perform some function, some activation function here, activation computation, some computation is happening here, and the output of this is passed as the input to the next level neurons, right? So output of this level neurons is passed as input to the next level neurons. Similarly, the output of this level neurons is passed as input to the next level neurons. Right. So isn't it looking like the biological neural network where the output of one neuron is input to the another neuron, even in case of biological neural network, isn't it? So this is the similarity between the biological neural network and the artificial neural network. Right. So let's try to understand a single neuron or a single artificial neuron. We also call it as a perceptron. Okay, so artificial neural network with a single neuron cell is equivalent to logistic regression model. We have already seen logistic regression model, right? If you remember, do you remember that we have already seen logistic regression model?
Yes, sir.
Right. So artificial neural network with a single neuron cell is equivalent to logistic regression. So first, let us try to understand the logistic regression with the neural network mindset. Okay, and then we'll extend this to neural network, neuron to a neural network. Okay, so right, why the strength is too low? Let me give me a minute. All right. So this is a single neuron where you're receiving inputs I1 to In or X0 to Xn. Right, X0 is 1, of course. So X1 to Xn, similar to the way we are receiving inputs in the case of linear regression or logistic regression. And these are the weights. Weights are equivalent to theta naught, theta 1, theta 2 in our notations. Right. And then what are we doing? We are computing the weighted sum here y equal to 0 to n wi times xi. So we're multiplying w naught with x naught, w1 with x1, w2 with x2, and so on. We're taking sum over that. So this we are calling it as a net sum. So once we get the net sum, this is the resulting aggregation. So once we get this, we are giving it a sigmoid function, 1 by 1 plus e power minus net. Right? So if this resultant is greater than certain threshold, then it is 1. Otherwise it is, if less than certain threshold, then it is 0. Right? So the outcome is either 1 or 0 after passing it to the sigmoid function. Right? So this is a single neuron. A group of these neuron units together forms a neural network. So this is a representation of the neural network. This is layer 1 where we are receiving the inputs. X1, X2, X3 are the inputs or the features, and A1, A2, A3 so on are the activation units at layer 2, and this you can also call it as A1, 3. Okay, so this is activation unit at layer 3. So this we call it as the input layer because that is the layer where we are receiving the inputs. And this layer 3 is the output layer because that is where we are giving the output. And this is the hidden layer. Layer 2 is the hidden layer. Right. And if you see the activation units, the notation of the activation units, for all the layer 2 units, we have got a superscript of 2. So the superscript indicates the layer number. Similarly, here also the superscript indicates the layer number. Similarly, x0 also can be represented as a a01, x1 also can be represented as a11. So the superscript indicates the layer number and subscript indicates the unit number in that particular layer. Right? So, so these are the simple notations that we're going to use in the coming slides. If you have only one hidden layer, we call it as a shallow neural network. If you have got more than one layer, more than one hidden layer, then we call that as a deep neural network. Deep neural network. And this is a multi-layer perceptron in which each neuron in the previous layer is connected to each and every neuron in the next layer. So suppose if you see this x1 or a1, right? So this A13 is connected to each and every unit in the previous layer, right? Similarly, A12 is connected to each and every neuron in the previous layer. It is a fully connected neural network. We also call it as a multi-layer perceptron. We also call it as a fully connected neural network or multi-layer perceptron or feed-forward neural network. Okay, so there are many feed-forward neural networks, but if somebody says feed-forward neural network, usually they means this multi-layer perceptron, feed-forward neural network. Okay, so any one of these names refers to this particular network. All right, so are you with me so far?
Yes, sir.
All right. Now the question is, why do we need neural network? We have linear regression, we have logistic regression, and why do we need neural networks at all? So let us look at how the linear regression or logistic regression learns the complex nonlinear hypothesis. Right? So linear regression, suppose it hypothesis is theta naught plus theta 1 x. So if you want to learn the complex nonlinear hypothesis, then you have to go for the second order polynomial or third order polynomial or fourth order polynomial and so forth. Right? So that's the way out, right? If you want to learn the complex hypothesis, right? Suppose if you go for the second order polynomial, your hypothesis would look something like this, theta naught plus theta 1x plus theta 2x squared. And if you go for the third order polynomial, your hypothesis would look something like this, theta naught, theta 1x plus theta 2x square plus theta 3 x cube. This is the case with linear regression, and this is true with the logistic regression also, right? So this is when you have only one input variable. What if you have two input variables? Then what would be the second order polynomial equation? Anyone? What are the different polynomials that we have to generate? X1 square, x2 square, x1, x2, all those combinations, right? Isn't it? Neural network gives weightage to features which has more of zeros. Ma'am, I didn't understand your question. Is it a question or are you saying something?
No, sir. You are asking why you wanted to use this neural network. So what I know, I've put it
Oh,
as
okay. You are answering that. Okay.
yeah.
All right. So we'll see that. We'll see that how it runs the complex nonlinear hypothesis very simply. Okay. So right. So if you go for the second order polynomial, suppose if you have two features x1 and x2, and linear regression with the first order polynomial is something like this: theta naught plus theta 1 x1 plus theta 2 x square, which we call it as a multivariate linear regression. If you go for the second order polynomial, you will have to generate x1 square, x2 square, x1, x2. So how many features here, or how many parameters that you need to learn with two features and second order polynomial? 6 parameters, right? Theta naught to theta phi. Okay. Suppose if you go for the third order polynomial, then you will have to generate x1 cube, x2 cube, x1 square, x2, x1, x2 square. All these features you need to generate with two features. So if you go for the third order polynomial with two features, you will have to learn 10 parameters. Okay, and this is true with logistic regression also. So now the question is, what if we have 100 features? What if we have 100 features and if you go for the second order polynomial, how many parameters you need to learn? How many parameters? 100 C2 number of parameters. Order of 100 C2 number of parameters, isn't it? It would be around 5000 parameters. What if you go for the third order polynomial? Around 17,000 parameters you need to learn just with 100 features. If it increases, just with 100 features and third order polynomial, it is 17,000 parameters that you need to learn. Suppose if you go for the higher order polynomial, or if the number of features are increasing, can you imagine the number of parameters that you need to learn? Or do you think it is possible? Or if it is possible, how long it takes to accurately learn to learn the optimal parameters for those many number of parameters? It would be very difficult, right? Agree? Learning of 70,000 parameters or more than that would be very difficult. Okay, and this is a very simple problem that we are looking at. In real time, we may have hundreds of thousands of features sometimes. And maybe you have to learn some complex models, like you may have to go for some ninth order polynomial or 10th order polynomial or something like that. Then the number of parameters that you need to learn will be very huge. Okay, and which is very difficult to learn for a model, and it takes very longer time to learn the optimal parameters in that case, and sometimes you may not converge to optimal parameters at all, right? So this is the problem with linear regression or logistic regression models. Okay, so now we will see how this artificial neural network solve that problem, how it learns this nonlinear, complex nonlinear hypothesis with a minimum number of parameters, with very few number of parameters. So that's what we're gonna see in the coming slides. Okay, so to understand this, let us take a simple example of the nonlinear case, nonlinear classification example. So all of you must be aware of this XOR or XNOR gates, right? XOR or XNOR. In an AND gate, OR
Yes,
gate,
sir.
XOR gate, XNOR gate, you are aware of all this, right? So
Yes, sir,
if
we have
both the
started.
input, yeah, very good. So if both the inputs are zero, XNOR gives the output as, sorry, if both the inputs are same, XOR gives the output as 0. If the inputs are different, it means one input is 0, the other input is 1. Then in that case, the output becomes 1. XNOR is the reverse of this. If both the inputs are 0, then the output will become 1. Otherwise, it is 0. So as you can see the tables, right? If both the inputs are 0, 0 or 1, 1, then XOR output is 0. And if they are different, then the output is 1. So the reverse is the case with XNOR. Okay, so let us take an example of XNOR. If both the inputs are same, then it is 1, otherwise it is 0. So this is how it can look like, right? If I say input 1 is x1, input 2 is x2, right? So if x1 and x2 are 0, so this is one case where y equal to 1, and if input 1 is 1, the input 2 is 1, and both the inputs are 1. So then is another case y equal to 1. So the output here is y, n1 is x1, n2 is x2. Right? If they are different, like either 0, 1 or 1, 0, so this is a different class. They belong to class 0. So we represented them with circles, and class 1 we have represented them with cross marks. Okay. So let's assume that we have generated the data from the same distribution, like the way we have seen in the second figure. So this is the data and this is how it is looking like. Right? So do you think it is a linearly separable data? Can you draw a line that separates circles from the cross marks? You cannot
No.
draw a line that separates circles from the cross marks. So therefore it is a non-linearly separable data, non-linear data. The data is non-linear in nature. So let us see how the artificial neural network learns this. So before that, let us try to model different gates, linear gates, using this artificial neural network. So to understand that, let us take a very simple gate, AND gate. Okay, so what would be the output of the AND gate? When it will become 1, when it will become 0? If both the inputs are 1, then only it is 1, otherwise it is 0. Isn't it? So the output of AND gate is 1 if both the inputs are 1, otherwise it is 0. Okay, so I have modeled this AND gate using a simple neuron, a single neuron. I have modeled this. It means using logistic regression, in fact, right? So I have used a single artificial neuron to model this AND gate. Okay, it means the logistic regression I have used to model this AND gate, right? So I've used different weights here. Sorry, ma'am, do you have any query?
Sir, sorry.
Yeah.
Sir, one question in the last slide. You have one more figure, no, sir? Is that something, the second figure, x1, x2? So that is something indicative here, or with lot of crosses and lot of circles here?
Yeah. You assume that the data came from the same distribution. So therefore, the points are around those points in the original space.
Okay, got it,
Yeah.
sir.
Right. So if I take the weights as minus 30, 20, and 20, what would be h theta of x here? H theta of x. So what would be the net sum first of all? Minus 30 multiplied by x naught plus 20 multiplied by x1 plus 20 multiplied by x2. This is the net sum, and x naught equal to 1. We know that. So this would be equal to minus 30 plus 20 x1 plus 20 x2. Now this is given to a sigmoid function z, right? Z of minus 30 plus 20 x1 plus 20 x2. And all of you know z of z is equivalent to 1 by 1 plus e power minus z. Okay, so now z is equivalent to this. Z equivalent to minus 30 plus 20 x1 plus 20 x2. Okay, so now let us substitute the different values for this x1 and x2. Okay, what if x1 and x2 is equivalent to 0? Both of them are 0. Then what would be z value? If x1 0, x2 0, x2 0, 0, what would be the z value? that would be equivalent to minus 30.
Minus 30.
And what would be z of z? Z of z equivalent to 1 by 1 plus e power 30. So what it is equivalent to? E power 30 is some big number, right? So therefore 1 by very big number is nearly equivalent to 0. Agree? Right? So z of z is equivalent to nearly equivalent to 0 in this case. So let us take another instance 0, 1. In this case, what would be the z value? 0, 1. Z value?
Minus 10.
Minus 10. Right, very good. So when you substitute this minus 10 in z of z, z of minus 10 is equivalent to 1 by 1 plus e
To the
power.
power of 10.
So which is equivalent to 1 by almost infinity. So very big number. So this is nearly equivalent to 0.
0.
Right, 1, 0. Z value is again minus.
Minus 10.
Right, and this is also equivalent to 0.
0.
And if I take 1, 1, in that case, z value is equivalent to
10.
10 and 1 by 1 plus e power minus 10.
Minus 10.
So this would be equivalent to 1, isn't it? Because this part is almost close to 0, so therefore this is equivalent to 1.
1.
Right? So isn't it the output that we are expecting for the AND gate? If both our inputs have 1, then only it is 1, otherwise it is 0. Right? So we have modeled the AND gate using a simple neuron, simple artificial neuron. Right? So let us take another example, OR gate with the perceptron. So I'll take different weights now here, minus 10, 20, 20. Earlier the weights are minus 30, 20, 20. Now the weights are minus 10, 20, 20. Okay. And h theta of x is z of minus 10 plus 20 x1 plus 20 x2. So when the inputs are 0, 0, what would be the z value here? x1, x2, z
Minus 10.
minus 10. And z of z is equal to 0. When the inputs are 0, 1, this would be equivalent to plus 10. Isn't it?
Yeah. Plus
Plus
10. It is
10.
1.
This is equivalent to 1. In the case of 1, 0 also, it is plus 10 and this is equivalent to 1.
1.
When it is 1, 1, this would be equivalent to 30 plus 30 and this is close to 1. So this is the outcome of R. If both the inputs are 0, then only the output is 0, otherwise it is 1. Right? So we have got AND gate, we have got OR gate, and let us see some more gates. NOT gate also you can define using these weights 10 and minus 20. So the output is 1 when the input is 0, the output is 0 when the input is 1. Right? Similarly, you can also define NOT x1 and NOT x2. So which is also you can model using a different weights 10, minus 20 and minus 20. So the output is 1 when both the inputs are 0 and otherwise it is 0. Okay, so if you see all of them, they are linear in nature. So all the examples that we have seen so far, AND gate or OR gate or NOT gate, NOT x1 and NOT x2 gate, all these are linear in nature. And you can model the linear problems, linear data using a very simple neuron, a single artificial neuron, which means using logistic regression, you can model them in fact. Right? Now, can we combine all these together and provide a solution for x1, x0, x2? Right? So putting them, all of them together, we'll get x1, x0, x2. Let us see how we do that. Okay. So this is AND gate x1 and x1 and x2. Right? So you can see this. The functionality of this neuron is AND gate. So if you see this, corresponding weights minus 30, 20 and 20. Right? So minus 30, 20 and 20. Correct? So this is the AND gate. Agree? And if you see this, this is a NOT x1 and NOT x2 gate. So if you see the weights 10, minus 20, minus 20. Here also 10, minus 20, minus 20. So this is NOT x1 and NOT x2 gate. So, and these are the outputs that we are getting. As the output of the AND gate, we are getting 0, 0, 0, 1, and as the output of not x1 and not x2 gate, we are getting 1, 0, 0. Right now, finally at the other layer, we are taking these two as the input, and we are applying a OR gate here. So this is a OR gate. You can see this, right? So this is minus 10, 20, 20. Okay, minus 10, 20, 20. Right? So this is a OR gate, right? And we have got the output as 1, 0, 0, 1. Okay, isn't it the output of XNOR? When I take X1, X0, X2, what would I get? If both the inputs are same, then the output should be 1, otherwise it is 0. Isn't it I'm getting here?
Sir.
1, 0, 0, 1.
Yes.
Right. So when you combine multiple linear models together in certain fashion, you would get a nonlinear hypothesis. Okay, so that's the beauty of this artificial neural network. So if you see this network, how many parameters you require to learn this? Sorry. How many parameters you require to learn this? In the whole network? 9. Okay, so 3, 3, 3. 9 parameters we require, right? So total 9 number of parameters only we are doing to learn this complex nonlinear hypothesis. So the drastic improvement on the number of parameters, right? So that is the reason why we need this artificial neural networks. So that is the motivation behind using this artificial neural network, right? So these are some of the notations that we're going to use in the coming slides. Okay, so this network has got 3 layers. Layer 1 is the input layer, layer 3 is the output layer, and layer 2 is the hidden layer. And X0 and A0 2 are the bias terms, like the bias units that we have in linear regression, right? When you compute W transpose X plus B is the bias there, right? So similarly, we have bias units here also. X0 and A0 2. For each and every layer, we have one bias unit. And layer 1 and layer 2 has got 3 units in each, right? Excluding the bias unit. 3 and 3, right? These are the sum of the notation. Superscript indicates the layer number, subscript indicates the unit number in that particular layer. And theta j is the matrix of weights controlling a function mapping from layer j to layer j plus 1. Okay, so layer j to layer j plus 1. So for example, layer 1 to layer 2, we have got theta 1, which is a matrix of weights here. And here we have got theta 2, which is also a matrix of weights. Now the question is, what would be the size of this theta 1 or theta 2? What would be the size of this theta 1 and theta 2? Okay, so if you say that theta ikj represents the edge weight between unit I in the layer j plus 1 and unit k in the layer j. Okay, so it means that if I say theta 1, 1, 2, okay, so which is an edge weight between a1 to a2, this one, a1 to x2, right? Brindan, she said something. Some border issues between. Okay, no problem. Right. So yeah, so this is the edge weight. Okay, theta 1, 2, 2 is this. Okay. Similarly, you can interpret the other weights. Now the question is, if the network has Sj units in layer j and Sj plus 1 units in layer j plus 1, then what would be the size of theta j? Okay, so if I say this is S1 number of units here and S2 number of units here. What would be the size of theta 1 is the question now. Size of theta would be S2 times, S2 by S1 plus 1. Okay, so where S2 is the number of units in layer 2, S1 is the number of units in layer 1 plus 1 bias unit. Okay, so what would be the size according to this? What would be the size of theta 1? What is the number of units in layer 2, excluding the bias unit? What is the number of units in layer 2, excluding the bias unit? 3, right? 3. And what is the number of units in layer 1, excluding the bias unit? It is again 3, right? So 3 plus 1. So the size of theta 1 would be 3 by 4. Okay. And what would be the size of theta 2 according to this? What would be the size of theta 2? 4. But what is that? 1 by 4 or 4 by 1? 1 by 4, right? Because S3 has got only 1 unit times S2 has got 3 units plus 1 bias unit, right? 1 by 4 would be the size of this theta 2. Alright, so this is how you can represent theta values. So in the vectorized notation we will use that. But before that, let us say a forward propagation. So we're starting with a layer 1. We are giving inputs here and we are computing the activation units at layer 1 and we are giving this activation units as the input for the next layer and so on. So this one pass we call it as a forward propagation. Starting from input layer and ending at the output layer, we call it as a forward propagation. Right? So if you see that at A1, 2 is x0, x1, x2, x3 multiplied by the corresponding weights and giving it to the sigmoid function. Okay, so you're computing net sum here by multiplying each and every input with the corresponding weight and taking sum over that, and then you are giving that net sum to a sigmoid function, z of z. So I've got A12. Similarly, I compute A22 by multiplying with the corresponding weights and taking net sum and giving it to the sigmoid function. Similarly, I compute A32, right? Taking net sum and then giving it to the sigmoid function. So once we get all the activation units at layer 2, right, we give them as an input for the next layer. So we compute this A13 here, which is the activation unit 1 at layer 3, which is also equivalent to output h theta of x. So h theta of x is our hypothesis or the model. Right, so h theta of x equivalent to A13, which is equivalent to z of A0 to A12, A22, A33 multiplied with the corresponding weights and taking net sum over that and giving it to the sigmoid function. So this is a forward propagation, one pass of the forward propagation for this particular network. So what are we doing here? We are starting at the input layer, computing the activation units layer by layer. And when you compute all the activation units at a particular layer, we are giving them as an input for the next layer. Okay, and we repeat the process and we continue till the output layer. Right. So once we go to the output layer, we get the prediction, which is our h theta of x. Okay, so we've got the prediction here, right? So if you vectorize this, you can write it this way, right? If you vectorize this, you can write it zz, which is the net sum is theta times a, that theta times a, which is equivalent to our theta transpose x or x theta we are writing in case of linear regression, right? So z is equivalent to that. So which is equivalent to x naught theta naught plus x1 theta 1 plus x2 theta 2, so on, something like that, right? So theta times a, where a is a1 is equivalent to x, right? At the input layer, it is equivalent to x. You can write activation at that particular layer is equivalent to z of zz. Right? So if you see this, we are computing the activation units at one layer at a time. All the activation units at one layer at a shot. Okay. And theta j minus 1 is the matrix of the dimensions sz times sz minus 1 plus 1. So this just now we have seen. So suppose if you want to compute z2, so which is the net sum here, net sum at this layer. So z2 is equivalent to theta 1 times a1. So where a1 is the activation units at this layer, which means x0, x1, x2, x3, and you multiply them with corresponding theta values, you would get z2. And when you give this to sigmoid function, you would get the activation units for the next layer, that is A2. A2 is equivalent to 0, Z2. Alright, so this is how you can compute. So if I write it here, if I write it this way, So Z2 is equivalent to theta 1 times A1 and sorry Z of Z2 sorry A2 is equivalent to theta sorry Z of Z2. And what would be Z3? Can anyone tell me? Z3 is equivalent to Z2, Z3 is equivalent to anyone? Are you following me?
Theta 210 into theta 2
Times
times
A2.
it.
A2.
A2, right? And what would be A3?
G of Z.
G of
Z3.
Z3.
Suppose if I have a layer 4 also, then what would be Z4?
Theta 3
3A3.
into Z3.
Theta 3 times A3 and
A4.
A4 is equivalent to Z of
G of
Z.
Z3. Z4.
So this is how the forward propagation works. Right. So what if you have multiple classes? So far we have discussed with respect to a binary classification problem. So is it compulsory order of parameter matrix theta in reverse order? Prashant, I didn't get your question. Can you elaborate?
Sorry, I think is that we are having order of matrix from J plus 1 to J, right? J plus 1 number of layers in J plus 1 cross J. But generally, when we visualize, a naive intuition will be like number of.
That is the interpretation.
Yes,
The point here is that you are multiplying the row of theta with the column of A. So to have
yes.
that interpretation, we have taken in the reverse way.
Okay.
So usually
So,
when you go for that naive way, that whatever that you are describing, that
yes,
the
sir.
individual weights will come like a column. So if you interpret it
Yes,
that way, so you have to take theta transpose when you are multiplying with A. So both are
yes.
same in fact. Yeah.
Okay. So
Yeah, it
that
all depends
only
on
our.
the interpretation. You need not restrict to this notation. So this is the
Yes,
notation that in general that people follow. But if you want to implement it in your own notation, if you interpret that as Sz times Sz plus 1, something like that, that also fine.
yes. So one more doubt is that bias that is only at input layer. No, so why to add it in other layers?
At every unit we get, because every layer we are assuming it to be input for the next layer, right?
Yes, sir.
Yeah.
Okay, okay. Okay, sir. Thank you, sir. Yeah, thank you, sir. Yeah.
Yeah. So if you go for the multi-class classification problem, the output layer will have multiple units, right? If you have 4 classes, then you will have 4 units at the output layer, right? And each one of them will give the probability that a class label belong to a particular label. So for example, the output here would be probability that it would be a pedestrian, probability that instant would be a car, probability that it is a motorcycle, probability that it is a truck, and so forth. Right. So if you go for the actual distribution, the distribution is true distribution is 1000 for pedestrian, and true distribution is car for 01000, 0100. And for a motorcycle, the distribution would be 0010. And can you tell me what would be the distribution for truck?
0, 0.
Last one.
Last one, rest of them are zeros. 0,
Yes.
0, 0, 1. Right? So, and we would be interested in minimizing the loss at each and every output node. Okay, so we'll compute the loss here. If you see this, I'll have a binary classification problem kind of that in each and every node. Okay, so I compute the loss here, I compute the loss here, I compute the loss here, also here, and I take some of that as a final loss. Okay, so if this is the cost function of the logistic regression, right? Minus 1 by m somehow are equal to 1 to n yi log h theta of xi, 1 minus y log 1 minus h theta of xi. So if I have only one output unit, in the last layer, only one unit in the last layer, which means the output layer, then I can directly go with this objective function. But if I have a multiple units at the output layer, then in that case, I have to take sum over the individual units. So this will come into picture, sum over k equal to 1 to k. Okay, so I'm taking the loss here, loss here, loss here, loss here, and finally taking sum over that. And this I am doing for each and every instance. So sum over I equal to 1 to n. And the regularization term here is, we will be computing it for all the weights throughout the network. So that is why we are starting with layer 1 to L minus 1 I equal to SL, where SL is the number of units at layer L. SL plus 1 is the number of units at layer L plus 1. So this basically gives all the parameters throughout the network. You're taking in the regularization term, right? So that's the only difference, right? The regularization term will include all the weights, right? And this will include k equal to 1 to k to generalize it to k classes. Right? So this is the cost function here. Okay. Now, so far it is good. Like, for example, we have discussed what is a neuron, what is the motivation behind the using artificial neural network, and what makes artificial neural network, like the set of neurons, layer by layer in certain fashion organized together, forming a neural network. Okay. So we have also defined the hypothesis through a forward propagation. Once we get the hypothesis, we have also defined the loss function at the output layer, right? So we are starting with the input layer by layer, we are computing the activation units, and finally we are arriving at the output unit. At the output unit, you are computing the loss function. That means the objective that you want to minimize. Okay, now the question is, how do you minimize this objective? We've got some loss, right, at the end of the output layer. At the output layer, we've got some loss. So what is your objective? Objective is to minimize the loss. How do you minimize the loss? How do you minimize the loss in case of linear regression?
Analytical or a computational method.
Yeah, so by using, we are adjusting the parameters of a model and minimizing the loss, right? We are learning the optimal parameters theta naught and theta 1 in case of linear regression, isn't it?
Yes.
So we are adjusting the parameters of a model and minimizing the loss. It means we are learning the optimal parameters, right? So the similar is the way here. We have got the parameters of the network, isn't it? We have got so many parameters of the network, layer by layer. We have got so many parameters. So the brute force way of minimizing this loss or learning weights is compute the gradient with respect to each and every weight and then apply a gradient descent algorithm to update the weights. Right. So for example, if I want to know, so this is the J. J is our cost function or the objective function. Suppose if I want to learn the optimal weight for theta 1, 1, 2. Okay, theta, sorry, let's say theta. Okay, theta 1, not a problem. Theta 1, 1, 2. What would I do? Theta 1, 2 equivalent to theta 1, 2, 1 minus alpha times derivative of j with respect to theta 1 to 1. Okay. Similarly, this I do for each and every weight in the network. So theta I j k is equivalent to theta I j k minus alpha times derivative of j with respect to theta j k I. Okay, so compute the gradient with respect to each and every weight. Apply the gradient descent algorithm to update the weights, and it is a very time intensive process and so many redundant calculation you will have to do if you do this. If you go with this brute force approach. Okay, so the same thing you may have to compute so many number of times. Okay, so what is the solution then? What is the solution then? Solution is backpropagation algorithm. Backpropagation algorithm. So what is backpropagation algorithm? It is a kind of dynamic programming and it avoids redundant computations. So those who have no idea about dynamic programming, I'll just simply describe it in the layman terms. So dynamic programming is a kind of algorithm where it computes once and stores it in a table. So every time when it computes some quantity, it stores in a table. Okay, whenever the next time the algorithm requires the same value, it will not repeat the computation. Instead, it will access from the table. Right? So isn't it the dynamic programming doing? Those who have idea about the dynamic programming? Dynamic programming is doing the same, right? It is
Yes, sir.
computing the quantities of interest and storing them in some table. And every time, when the next time it requires the same value, it accesses from the table. So it avoids the redundant computations. The same thing we do in case of backpropagation algorithm. Okay, so let's see how we do that. Before that, let us try to understand what is the backpropagation algorithm, the procedure of the backpropagation algorithm. So forget about how is it doing now. Let us just try to understand what is backpropagation algorithm. So we'll later see how these redundant computations are avoided and all that we'll see later. But before that, let us try to understand what is brute force approach. Backpropagation approach, backpropagation algorithm. So forward propagation is this. You are starting with the input layer A1 equal to X. So initializing the activation units at layer 1 to the inputs. Right. So A1 equivalent to X. Then computing Z2, which is theta times A1, theta 1 A1, A2 equivalent to Z of Z2. This is after adding A0 2, by the way. Okay. So to this add A0 2 and after this you add A0 2. After computing A2, you compute A0 2 and together you compute Z3 and so Z3 is equivalent to theta 2 A2. So this is after adding A0 2. The A2 is after updating with A0 2. Right, and A3 is equivalent to Z of Z3 and so on. L minus 1, where capital L is the number of layers. Okay, so L minus 1 is equivalent to Z of ZL minus 1 and ZL is theta L minus 1, AL minus 1. And finally, activation unit at the output layer AL, which is equivalent to our hypothesis or the prediction, which is equivalent to Z of ZL. Okay, so this is forward propagation. We have already seen this. Okay, now let us try to understand backward propagation. Backward propagation, right? So what is a back propagation? Suppose um, let's suppose we are organizing this workshop FDP. Okay, so group of people together organizing this. Okay, let's say X, Y, Z. X, Y, Z organizing this, and X has kept an effort of 70%, Y has kept an effort of 20%, and Z has kept an effort of 10%. Okay, so if something goes wrong in the output, in the outcome, okay, so in what percentage this X, Y, Z should share the blame? If something goes wrong here, in what
Weighted.
weight, right? So X will take 70% blame, Y will take, yeah, in the same proportion you're able to take, right? So if you see this weights, theta values at different layers, okay, in between different layers, right? So there's so many weights finally together contributing to the final prediction, right? So the activation units and the weights together contributing to the final prediction. Okay, if the prediction is wrong, then that error should be back propagated to the previous layers, isn't it? Isn't it? So in a forward propagation manner, you're getting the prediction and you're realizing that there is some error in the prediction. So this error should be propagated back to the previous layers such that they will adjust the weights and lead to the minimum error or minimum loss, isn't it? Right? So that is what the back propagation algorithm is doing. So in a forward propagation manner, we're computing the hypothesis and finally we are getting the loss. And this loss or the error is propagated back to the previous layers. Right. So for this, we are assuming that the just for the simplicity to explain, because if I assume it to be objective function to be this entropy loss, the one that we have seen, then it would be difficult to explain. So that for that reason, I am assuming the loss to be a square loss function. Okay. So later I will explain the generalization of it, but for now assume that the loss function is this square loss. And you need not, I mean, you may not even realize that, but just I'm telling you that the loss function is assumed to be a square loss in this from now onwards. Okay. Right. So H theta is the prediction and AL, H theta of x or AL is the prediction. And in order to reduce the error between the prediction and the actual value, backpropagation is used. Okay. And let's say delta JL is the error of node J in layer L. Okay. And it is associated with the prediction made at that node given by AJL. Right? So forget about all this. You may a little confused. Forget about all that. You will understand it gradually, no problem. So you're computing prediction, which is h theta of x, or you call it as AL also, right? Activation unit at the last layer. Okay, and this AL has got different units. It has got AL1, AL2, like that. Right? So what would be the error here and what would be the error here and what would be the error here and so on. How do you compute? The error is the difference between the actual and the predicted, right? Difference between the predicted and actual, right? So can I say the error delta Lj is equivalent to Alj minus Yj? If you vectorize it, delta L equivalent to Al minus Y, which is the difference between the prediction and the actual value, which is the error at the last layer. Okay, so this is the error at the last layer. Now you have to propagate this error back to the previous layers. Okay, so the backpropagation algorithm is doing that. So error at the last layer is delta L times delta L equivalent to AL minus Y. So as I have told you, please understand, try to understand the procedure first. Do not think about why is it, how is it, all that. We'll understand that in later slides. Don't worry about that. So just try to understand the procedure blindly. Understand the procedure. I'll explain you how and why later. Right? So the error at the last layer is AL minus Y, which is delta L was saying. Okay, now you are propagating this error term back to the previous layers and computing the error at the previous layers. So which is equivalent to delta L transpose, sorry, theta L transpose delta L plus 1. Right? So you are taking the error from the previous layer, which means when you're coming back the previous layer, which means the next layer when you're going forward. And this error multiplied with the corresponding weights is computed here. Delta L transpose, sorry, theta L transpose delta L plus 1. Okay, and times z dash of zl. So g dash of zl is derivative of z of zl with respect to zl. Okay, so this gives you the error at layer L. So this error is computed from the next layer error. Okay, so the delta L plus 1 is the next layer error. Okay, so propagating it back to the previous layer, right? So this is how you are computing the errors at each and every layer. So you have computed errors at delta L minus 1, so on, delta 2. Okay, so this backpropagation algorithm stops at layer 2. Can you tell me why? Can anyone guess? Why is it? Why it should stop at layer 2?
Because for linear, for degree 1, there will be no.
For L equal to 1, there is no error because it is an input layer. So inputs cannot be modified. Yeah, good. right? So that is the reason why we are stopping at L2. So we do not assume that there is an error in the input. Okay, so that is why we are stopping at layer 2. Okay, so if you see this, now we are directly computing the gradients. So this is the procedure to compute the error at layers. Layer L1, layer L2, layer L3. You're starting with the output layer, propagating the error to the previous layers. So you're starting with delta L, computing delta L minus 1, so on, delta 2, using this procedure. So once we get the error, we can directly compute derivative of j with respect to theta ij as ajl times delta I L plus 1. Okay, so this is the direct formula. Using this, you can directly compute the derivative of j with respect to theta ij L. Okay, so you need not take actually derivative of j with respect to each and every theta value. You do this backward propagation. Once you do the backward propagation and compute the error at each and every layer, you use the error term to compute error term and the corresponding activation units to compute the derivative of j with respect to theta ij f. Okay, so this is the procedure. Let us summarize that. We have given a training set x1, y1, so on xm, ym, and we are just initializing this theta ijl, delta ijl values to 0, which is the derivative part. Okay, gradient parts. Theta ijl are the gradient part at that particular theta ijl value. Okay, so for all the instances for I equal to 1 to m, you are setting a1 to xi. Okay, which means the input layer is this a1, right? And we are performing forward propagation and computing a2, a3, so on, al using forward propagation. We have already seen how to compute that. Once we compute the forward propagation at last layer, you will get the prediction. AL is the prediction. So now compute the error at the last layer. So here you compute the error delta L. So once we compute the delta L using the backward propagation algorithm, compute delta L minus 1, delta L minus 2, so on, delta 2. Okay, so if you see that you are starting with A1, A1 is X, and computing A2, A3, so on, AL in a forward propagation. And at the output layer, you are computing the error, which is delta L. And using this delta L, you are computing this delta L minus 1, delta L minus 2, so on, delta 2 using backward propagation. Okay, so once you get both this delta L and AL values, so use both of them, AL and delta L. So you need not repeatedly calculate them. You're just using them and updating this theta ijl is equivalent to theta ijl plus ajl times delta ijl. So why? This is equivalent to derivative of j with respect to theta ijl. Okay, so this you are adding it for all the instances I equal to 1 to n. Okay, so for all I say you are doing this, right? So once you do this, so you have to take the average to finally get the gradient, isn't it? When you are updating theta values also, theta I equivalent to theta I minus alpha times derivative of j with respect to theta j. So that is equivalent to this sum over I equal to 1 to n. You are considering all the instances, right? Right? 1 by m sum over I equal to 1 to m and the derivative part, isn't it? So similarly here also we do that. So this is a vectorized implementation, by the way. Delta L equal to delta L plus small delta L plus 1 AL transpose. Right. So we take that and take the average. Here also average. And this is the regularization part, because when j equal to 1, we will not have any regularization part. This is just 1 by m delta ijl. Okay, so finally you set derivative part to dijl. Right? And we update the each weight using the gradient descent algorithm. We update like theta ijl equivalent to theta ijl minus alpha times derivative of this dijl, which is the derivative of j with respect to theta ij. Okay. So this is the procedure. If you have any query in the procedure, ask, then we'll see why is it equal and how is it equal. We'll see in the coming slides. So have you understood the procedure? Are you with me so far? Are you overloaded with the mathematics? Have you understood the procedure?
Yes, sir.
Okay, so we're doing forward propagation, slightly overloaded, Shekhar. Okay. So you want me to repeat something?
So can you repeat last part?
Last one, that averaging thing, right?
Yes, sir.
Okay. Okay. So this, till here you have understood, no? Forward propagation and backward propagation and computation of this AJL delta IJL. Have you understood till there? We are doing forward propagation, computing A2, so on AL, doing backward propagation, computing delta L to delta 2. Once you get that, you get derivative of J with respect to theta IJL as AJL times delta I L plus 1. Okay, so this procedure you repeat for all the instances I equal to 1 to n, I equal to 1 to n. Okay, so the final value with respect to derivative of J with respect to theta Ij is the average over all these instances derivative. Okay, so derivative of J with respect to theta Ij. Right. So this you are doing for this theta Ijn, you are doing for I equal to 1 to n. And computing all the derivatives, derivatives with respect to this single instance. Okay. Finally, taking sum over all the individual instances. You're initializing them to 0 and adding at each and every instance. I equal to 1 to n. Okay. Once you add, you take the average. That's all. So take the average 1 by m delta ij. And this part is for the regularization term. Right, when you take the derivative with respect to regularization term, you would get this. So for j not equal to 0, you have to add the regularization term also. And j equal to 0, because in regularization term, we don't take theta naught values. We will not have theta in the derivative part, theta naught in the derivative part. That is why we are not adding anything, just simply taking average of the individual values. Right. So when you take the average, you have got the final derivative of j with respect to theta ij. Okay, so use this gradient to update the weights. Okay, so like this, theta ijl equivalent to theta ijl minus alpha times dijl. Okay, where this is the derivative of j with respect to theta ijl over all the instances. Average over the all the instances. So have you got it now? Or any other query you can ask, please.
Sir, is that M is the number of classes, sir? Right, sir.
M is the number of instances.
Okay, okay. Okay.
Sir, is
Thank
there
you.
any scope to apply Markovian approach to this artificial neural network?
Which approach, madam?
Markovian approach.
Markovian. Markov process.
Markov approach, sir.
Markov process.
Yeah.
That is for sampling, madam, actually. Not for this.
And if you assume, if you considering
The
0 and 1 binary.
randomization is involving, and if you have a huge data and if you wanna estimate something, then you are talking about hidden Markov models, huh?
Yeah.
Okay, okay, okay. No, ma'am, no. That is
Okay.
different. Yeah.
Okay. Okay.
So yeah, I thought something else. Sorry for that. I'm confused. Okay.
So in general, gradient descent, we don't do we perform an average over instances, and I mean, why there is a requirement over here? That is what I'm unable to relate here.
In general, can you repeat your question?
In general, in a normal gradient descent, for example, if we take for one layer logistic regression, which is nothing but one layer
Linear
neural
regression or
network.
logistic regression, yes.
Yeah. So there, if we perform a gradient descent on our optimize this objective function, loss function,
Hmm.
so we take the we update the weights parameters, but we don't take any average over instances.
We take there also. You want me
Okay,
to show
okay,
that?
okay. Maybe
Give
I
us
overlooked. Yeah, okay,
give a second, I'll show you.
okay, sir. So introduction of average makes me confused here.
Don't worry, no. I'll show you that.
Yes, yes,
Let
thank
me
you,
take
sir.
linear regression. Linear regression also okay, right?
Yeah, fine, sir. Anything works fine.
If it is gradient descent, we take average, but stochastic gradient descent, we don't take. I'll show you that.
Yes, sir.
Right. You can see this, right? 1 by m sum or equal to 1 to n yi dash minus yi xij. Isn't it the updation rule that we are doing
Yes, sir. Yes, sir.
in case gradient? Are we taking average or not? So this is with
Okay, but
respect.
average is
This
implicit in the derivative.
Yeah, it is implicit in the derivative. Yeah, implicit in the derivative because you are considering all the instances. Suppose if you don't consider all the instances, only one instance at a time, then it would be like this only, like in case of stochastic gradient descent.
Okay,
So if
okay,
you
okay.
yeah, so that's what I've told you also that time, no? If you're considering
Yes,
all
yes.
the instances to update theta value, then you have to take some average over.
Yes, sir.
Yeah, so you can see here.
So this is the case here also.
Yeah, here also you're taking that 1 by m sum over. So this is for one instance, and you're taking
Yes,
sum over that and average of that.
yes, sir.
Okay, right.
Yes, yes, sir.
So is that clear now?
Yes, sir.
Yeah. So this is the procedure. Okay. Now you may be getting doubt that how come this derivative of j with respect to theta ijl is equivalent to the simple formula ajl times delta il plus 1. Okay, how come it is possible? Right? So let us see that through example. So let us demonstrate using an example. I've taken very simple network, 2 units at the input layer, 2 units at the hidden layer, and 1 unit at the output layer. And I've also ignored the bias terms just for the simplicity. Okay, so I've ignored the bias terms. Right. So assume that bias is 0. Right. So Z12, which is the net sum at this layer, is equivalent to theta 111 times x1 plus theta 121 times x2. Right. So multiply this with this with this, and take sum over that. And that would be Z12. When you give this net sum to a sigmoid function, you would get the activation unit at this point, A12. Right? Similarly, you compute the net sum here, right? Z22, right? And then give it to the sigmoid, A22 you will get. Right? Now, once you get A12 and A22, you compute Z13, which is activation units multiplied by the corresponding weights, take sum over that, right? Which is this theta 112 times A12 plus theta 122 times A22. And when you give this to a sigmoid function, you would get A13, which is this, which is also our prediction H theta of x. Okay, so is this clear? The slides are not changing.
Clear, sir. Yes.
Clear,
Okay,
sir.
let me stop sharing. Now, can you see this?
Yes, sir, it was visible, sir. It was changed.
Okay, demonstration using example. Is that the slide that you're seeing?
Yes, sir.
Yes, sir.
Okay, right. So this is a forward propagation. You're computing Z1 to here, net sum here, net sum here, and then giving it to the sigmoid function. So after computing Z1 to, you're giving it to the sigmoid function, you're getting A12. And after computing the net sum here, you're giving it to the sigmoid function, then you're getting A22. And using this as an input, you're computing the net sum for the next layer, Z13, and giving it to the activation function, sigmoid function, then you're getting A13, which is our prediction. So this is a forward propagation. Okay, if you have any query here, you can ask me now. Following me? Have you understood this forward propagation? How we compute this forward propagation?
Yes, sir.
Right, great. So let us go to the backward propagation. So let us.
Oh, sir, excuse me.
Yeah.
In the previous slide,
Hmm.
is it here theta 12 or theta 21 here?
The first one.
Z22. Z22.
Yeah, this is theta 12, ma'am. We give first output layer number, then the input layer number.
Sir, in the slide it is written as theta 21. That's why. Here.
No, ma'am, this is theta 12. So this is theta 1 Okay, theta superscript 1, it means that it will in between layer 1 and layer 2. And the subscript 12 means it is the first one indicates the output unit, the second one indicates the input unit. Okay, so because the output unit is 1, this got 1, and the input unit is 2, that is where we got 2, 1, 2.
Okay. Thank you, sir.
Yeah. So, any other query? Right. So, following me so far? Are you with me so far?
Yes, sir.
Right. So now we have derived one backpropagation algorithm, no? According to that, derivative of j with respect to theta ij is ajl times delta il plus 1. So this is what we have seen, right, in the backpropagation algorithm. Derivative of j with respect to theta ijl is ajl times delta il plus 1. Okay, so let us try to derive whether we are getting that or not. Okay, so this is my j. Because I've got only one output unit, this would be equivalent to minus sum over equal to 1 to m y log s theta of xi plus 1 minus y log 1 minus s theta of xi. So this is the logistic regression objective. Because I've got only one output unit, this is equivalent to that. Right? So this is my objective, and I would like to derive this objective with respect to this theta 112, which is this weight, theta 112. Okay, right. So derivative of j with respect to theta 112. I've written this using the chain rule as derivative of j with respect to h theta of x, derivative of h theta of x with respect to z13, and derivative of z13 with respect to theta 112. Using the chain rule, I have written into three parts. Derivative of j with respect to theta 112, I have written it as using chain rule. Derivative of j with respect to h theta of x, and derivative of h theta of x with respect to z13, and derivative of z13 with respect to theta 112. So let us try to solve these individual ones. Let us start with this derivative of j with respect to h theta of x, and this is j. Okay, so this is j. Right? So if I take the derivative of j with respect to h theta of x, right, what would I get? What is the derivative of log x with respect to x?
1 by x.
1 by x, right? So y times derivative of log h theta of xi with respect to h theta of xi, which would be equivalent to 1 by h theta of
1 by
xi,
h2.
right?
Yes, sir.
Plus
Yes.
1 minus yi, 1 by 1 minus h theta of xi, and derivative of this 1 minus h theta of xi, which is equivalent to minus 1. Right? So this would be equivalent to yi minus h theta of xi divided by h theta of xi times 1 minus h theta of xi. I've got this if I solve this. So this is this. So let's take this one. derivative of Z13 with respect to theta 112. What is Z13? Z13 is this theta 112 times A12 plus theta 122 times A22. If I take derivative of this with respect to theta 112, what would I get? This part becomes 0.
A12.
I would get just this A12. Okay, so if I solve this part, I got A12. So what left? Derivative of h theta of x with respect to Z13. Okay, so let's try to solve that. What is h theta of x? H theta of x is z of Z13, isn't it? H theta of x, or you can also call it as A31. So A3 is equivalent to C of Z3, right? So H theta of x equivalent to C of Z13. Okay, so now let us try to generalize this. Suppose if I want to take derivative of sigmoid of x with respect to x, what would be the results? Isn't it in the same form? This one? Derivative of z of Z13 with respect to Z13. Isn't it in the same form? Derivative of sigmoid of
Yes,
x
sir.
with respect to x. So let us try to solve this, right? Derivative of sigmoid of x with respect to x. So if you solve this using this procedure, you would get derivative of x, sigmoid of x with respect to x. Sigmoid of x with respect to x, you call this as a sigmoid dash x. So this and this are equal. Is equivalent to sigmoid of x times 1 minus sigmoid of x. So now can anyone tell me what would be this derivative of h theta of x with respect to Z1? This would be equivalent to
H theta of x into 1 minus h
z of,
theta of x.
yeah, Z13 times 1 minus z of Z13, isn't it? So z of Z13, I'm just substituting sigmoid of Z13 times 1 minus sigmoid of Z13. Sigmoid of Z13 is h theta of x and 1 minus h theta of x. So I've got this now. So let us try to substitute them together. When I substitute them, yi minus h theta of xi, h theta of xi times divided by h theta of xi times 1 minus h theta of xi. If you see this term we have got in the numerator here, isn't it? When you multiply this and this, both of them will get cancelled. H theta of xi times 1 minus h theta of xi. This and this will get cancelled. Agree?
Yes, sir.
Right. So we'll
Yes.
left with yi minus h theta of xi. Other one is a12. So the resultant is yi minus h theta of xi and a12. Right. So this is y minus h theta of x and a12. And remember, y minus h theta of xi is the error at the last layer, isn't it?
Yes, sir.
Delta L, right? So
Yes,
delta L, which means delta 3 in this case, delta 3 times A12. I've got this as a resultant when I derive it manually. Okay, so let me see what the backpropagation algorithm is giving. If I substitute, so A1L. So what is this derivative of J with respect to theta 112? Theta 112, it means L equivalent to 2. Correct? L equivalent to 2. And what is J value? J value is 1. And what is I value? I is
I
also
is also 1.
1. Substitute that. When I substitute, what would I get? A12,
A1 2,
delta 1,
delta 1, 3.
3. Right? So isn't it the same? Delta 1, 3, A1, 2.
Yes.
Right?
Yes, sir.
Say, so whatever that you are getting through backpropagation algorithm and whatever that you have done through manual procedure, both are same. Okay, so is that point clear?
Yes,
Right.
sir.
So another thing that you can see is that if you go through this procedure, all these redundant calculations, to some extent, here you can see that you can realize to some extent, can be avoided. What are the redundant calculations? You need not compute A12 again because you can store it when you're doing forward propagation, you can store that. And delta 1, 3, this also can be stored, need not compute it again, right? So let me see one more, let me show one more example to you. You'll get more realization about this redundant computation avoidance. Okay, so let me see with respect to delta 111, which is this delta 111, which is at the different layer. Okay, so if I do this with respect to delta 111 using chain rule, I can write it as derivative of j with respect to a13 and derivative of a13 with respect to z13 and z13 with respect to a12, a12 with respect to z12 and z12 with respect to theta 11. Okay, so if you take these two together, what is this? Derivative of j with respect to z13, isn't it? Derivative of j with respect to z13, isn't it? We have already computed here. Derivative of say with respect to z13, this part we have already computed again, isn't it? We have already computed that this part, this we have computed, this we have computed,
Yes,
so
sir.
we have got this. So do you have to compute it again? You need not do that, right? Right? And similarly, this derivative of say z1 z13 with respect to a12 is this, and when you compute derivative of a12 with respect to z12 is this a12 times 1 minus a12, and z12 with respect to this is a1. So if you bring it down, this is the error term, which is the delta L plus 1, and this is theta L, and this is z1 dash L, this is a1. Okay, so all this together is giving you this backpropagation algorithms formula. Okay, and you can see this that whenever you're computing for theta 112, there are some redundant calculations for theta redundant calculations with theta 112, 121, sorry 112, yeah, theta 112. So these redundant calculations can be avoided if you go through this backpropagation algorithm. Alright, so that is how this backpropagation algorithm avoids the redundant computations. It just computes them once and uses them again and again. Okay, so the derivative calculation, gradient calculation with theta 111, derivative calculation with theta 112 is some part of the calculations are already done here so that you can reuse them when you are doing it for theta 111. So that's the motivation behind this backpropagation algorithm. So this way you can efficiently compute and very fastly you can compute, okay, as compared to the brute force approach. So that's the motivation behind backpropagation algorithm. Okay, so I'll be happy if you have got this motivation behind this backpropagation algorithm.
Yes. Yes.
Yeah, Prashant, if you have query, ask.
Yes, sir. Sir, in this notion, now the concept is clear, sir. Just one doubt, sir. But here, the theta L you have written, is it a vectorized form or what?
Yeah, you're traced.
Okay, okay.
Generally, I've written, but you can, yeah.
Yes, thank you, sir.
All right. So any other query? So there are lots of applications of this ANN. Almost in every domain we have applications applications of deep learning and artificial neural network. You can do character recognition, you can do signature verification, face recognition, machine translation, that is translating from one language to another language, speak recognition, translating from speech to the text. And almost in every domain we have the applications of AI. Like you just say simple feed-forward neural network, you have to explicitly extract the pages. But if you go for the convolutional neural network, it automatically extract the pages. So this is a case where explicitly extraction of the features. ODI character recognition. There are 5 important parts in the ODI character, right? As you can see in the boxes. Boxes are the 5 important regions of the ODI character. And these 5 important boxes are projected in 4 different directions: horizontal, vertical, right, left, all the different directions when it is projected, and summing over the black pixels in that direction. So that is one feature. So 5 boxes, 4 different directions, you will get 20 features. So only 20 features and 133 number of classes. And we have got around 10,000 instances, 95% accuracy around, right? So this is a very simple example. Particularly like this, you can apply to many instances. There's some of the differences. Thank you and happy learning. Demonstration is also there. If time permits, at the end of the session, I'll demonstrate. Otherwise, I'll share the code with you. It is very easy. You can go through it. And yeah, if you have any query, I'll take. Otherwise, we'll take some 10-minute break and come back. Any
So
query?
what is interpretability of neural? Then generally they say that neural networks have the drawback of neural network is that there is problem of interpretability of results. I mean, what is interpretability in neural networks, and how can we measure or how can we conceptualize it? I don't know if it is out of scope, but just
Yeah,
that.
yeah. Nowadays, this explainable AI is coming, no? So explainable deep learning is also coming. Like explainable neural networks also coming, which is a slightly different concept. It takes a lot of time to explain.
Yes. So when we compared with a neural network, we say that for larger complex nonlinear models, it is a better form because it has less parameters to learn. So,
Mm-hmm.
but what about support vector machines? I mean, even support vector machines fall
Yeah,
into the
yeah,
same
all of
category.
them, all of them.
Yes, yes. Sir. Thank you, sir.
Sir, what are deep neural networks?
Deep neural network has so many frameworks. This is one of the framework. Whatever that we have discussed, the speed forward multi-layer perceptron is one of the framework among them. So if the neural network has got more than, 2 layers, then we call it as a deep neural network. It means the number of hidden layers are more, then it is a deep neural network. If the number of hidden layers is few, like one, then we call it as a shallow neural network. Okay, but there are different architectures. They're not restricted to multi-layer perceptron. We have seen the fully connected neural network. No, every neuron is connected to every neuron in the next layer, right? So this is a fully connected neuron, right? There is a sparsity of connections in the convolution neural network, where you will reduce the number of parameters more reduction in the number of parameters. There are different frameworks like convolutional neural network, recurrent neural network, autoencoders, encoder decoders, generative adversarial neural networks, deep reinforcement learning. There are various frameworks. In each of these frameworks, number of hidden layers are more. So if you just simply want me to tell in one words, the number of hidden layers are more in this. But how these operations are performed is different, varying from framework to framework. In convolution neural network, we perform this operation in one way. In recurrent neural network, in a different way, like that. Okay, but deep means more number of layers in one word. Is that clear, sir? Okay, so let's take a break and come back by 6:45, right? And then we'll discuss clustering.
Yes.
All right. Thank you. Yeah, welcome back. Am I audible?
Yes, sir, you're audible.
Thank you. So is my screen visible? Clustering techniques?
Yes, sir, it is visible.
Okay, thank you. So let's start the second section, which is on clustering techniques, which is a kind of unsupervised learning where we do not have label information. So from the unlabeled data, we're trying to find the patterns or the hidden groups in the data. So this is a clustering technique. So in this session, we're going to see what is clustering, different challenges of clustering and applications, and different types of clustering techniques. So what is a cluster? So what is a cluster? Collection is a group of data objects. Cluster is a group of data objects such that the objects in one cluster are similar to one another and objects from two different clusters are dissimilar to one another. It means what? The objects that belongs to one cluster must be from a minimum distance from one another. Excuse me. Excuse me. It means that the distance between points from a single cluster is minimized and the distance between the points from two different clusters should be maximized. So we call the first one as intra-cluster distance. Intra-cluster distance is the distance between points belonging to the same cluster. Okay, so like this is the intra-cluster distance. Inter-cluster distance is the distance between the points from two different clusters, right? So the intra-cluster distance should be minimized and inter-cluster distance should be maximized. So you have to group these points in such a way that the intra-cluster distance is minimized and inter-cluster distance is maximized. Right. So clustering is a technique for finding such groups, finding groups of objects such that objects in a group will be similar to one another and objects from different groups are dissimilar to one another. And clustering is an unsupervised learning technique because we have no labeled information here. Right? So if you take this data set, it has got three natural groups of data points. So this is one group, this is another group, and this is another group. And the notion of cluster can be ambiguous sometimes. So for example, if I take this, how many clusters do you have in this data set? How many? 3. Okay, so some may say 3, some may say 2, some may say 4, like some may say 2 clusters, right? So somebody, Shekhar has seen 6 clusters, right? So 6 clusters or 4 clusters. So the notion of cluster can be ambiguous sometimes. And what is a good cluster? Good cluster is a cluster that the high intra-class similarity and low inter-class similarity. Right? Or in other words, low intra-class distance and high inter-class distance. So the quality of clustering results depends on both similarity measure used and the method and its implementation also. So the similarity measure used by the method and its implementation both will reflect in the quality of the cluster. So there are different applications of cluster. Like in case of business intelligence, you can use clustering technique to organize the customers into groups and develop business strategies for enhanced customer relationship management. Like for example, you can group all middle-aged persons or teenage persons or senior citizens. So not necessarily that way, but similar users can be grouped together and you can develop a business strategy for them and you can make recommendations for them accordingly. Right. So that improves the customer relationship management. You can also use this in image pattern recognition, like you can cluster handwritten digits, or you can compress the image, like represent the image with a limited number of colors. So instead of representing the image with so many number of colors, you group the colors. and represent with a limited number of colors. So this application we'll see at the time of demonstration. We'll also see handwritten digits classification. And then you can also use this in web search to organize the search results into groups and present the results in a concise and easily accessible way. And you can also use this in biology for determining group structure, that is population of cells or microarrays gene expression data. You can use it in security to identify fraudulent behavior. I mean, if you group all the normal behaviors into one cluster, then the outlier points will give you the fraudulent behaviors. There are many other applications of clustering exist. Okay, and what are the requirements of a clustering algorithm? Suppose if you are developing a clustering algorithm, if you are proposing some new clustering technique, what are the requirements of a clustering? It should be scalable. So many of the algorithms works very well with the limited number of instances or the limited data when the size of the data is small. But when the size of the data increases, they fail. Okay, so the algorithm should be scalable both in terms of the accuracy, in terms of the time also for the big data, for huge amounts of data, and ability to deal with different types of attributes. So many of the algorithms they are defined for the numerical data, right? Whereas in general, we may have different types of data like categorical data, we may have ordinal data, different kinds of data we have, right? So our algorithm must be able to deal with different types of attributes. Discovery of clusters with arbitrary shape, and clusters need not be of ellipsoids all the time, right? It can be of any shape. So algorithm should be able to detect the clusters with arbitrary shape, and minimal requirement for domain knowledge to determine the input parameters. So some of these algorithms, we need to pass some of the input parameters, like input parameter could be number of clusters, or input parameter could be the minimum number of points. Right, there are different parameters that each one of these clustering algorithms take. To determine those parameters, minimum domain knowledge must be required. Okay, so you need not know details of domain to apply a particular technique. An ability to deal with noise and outlier points, and you should be insensitive to the order of input records. You should be able to deal with high dimensionality. With 1-2 dimensions, many of the methods work, but if you increase the number of dimensions, all of them would fail. So you should be able to deal with so many number of dimensions. And incorporation of user specified constraints. Sometimes user may have some specific constraints. So the algorithm must be able to incorporate those user specified constraints. So algorithm must be flexible enough to incorporate the user specified constraints. And it should be interpretable and usable. Right. So these are the requirements of a clustering techniques. There are majorly four types of clustering techniques are there. There are hundreds and thousands of clustering techniques are there. It is not possible to discuss all of these clustering techniques in one session. So instead, we have partitioned these algorithms into four types: partitioning based algorithm, hierarchical algorithm, density based, and grid based algorithm. We'll discuss one each from partition based, hierarchical, and density based clustering techniques. So partitioning clustering, construct various partitions and then evaluate them by some criterion, like for example, inter-cluster distance or intra-cluster distance, minimized or maximized. So some criterion they evaluate. Hierarchical algorithm, they create a hierarchical decomposition of the sets of data using some criterion. Like for example, usually there is a naturally there is a hierarchy of hierarchical organization of the objects in many of the applications. Like for example, if you go to the library, all books may be one side, all journals may be another side. And inside the books, all computer science books are at one place, all civil engineering books are at one place, all mechanical engineering books are at one place. And again, if you go to the computer science books, Then all the artificial intelligence books are at one place. Database management system books are at one place. Operating system books are at one place. Like that, there is a natural hierarchy of groups in the many of the applications. So hierarchical clustering algorithm, it creates the hierarchical decomposition of these data points using some criteria. And density-based clustering is defined as a maximal set of density connected points. So based on the dense region of the points, it identifies the clusters. So wherever the points are densely connected to each other, where there is dense connectivity between the points, it makes them as a one cluster. We will see one of the density-based clustering algorithm, DB-scan algorithm. Grid-based, these algorithms partition the data space into finite number of cells. Once the cells are partitioned to form a grid-like structure, then we form the cluster from cells in the grid structure. Okay, so it doesn't depend on the number of points inside the cell once you divide the cells. It depends on the number of cells. Okay, so that way the algorithms would be more faster in case of grid-based technique. You can even parallelize them also. So grid-based clustering techniques are highly scalable in general. And the clusters corresponding to the regions that are more dense in data points than their surroundings. So these are the four major clustering approaches. Let us try to discuss each one of them one by one. Partition, hierarchical, and density-based clustering technique. So let's start with partitioning algorithms. Right. So are you with me so far? Is it fine? Is the pace? All right. Okay. Cool. So partitioning clustering algorithm. They construct the partitions of a database of n objects into k clusters. So they partition n objects into k clusters. Give me a second. Sorry, Madan. So they divide the n objects or partitions the n objects into k clusters. Okay. So the partitioning clustering algorithm usually adopts an iterative process. It means initially they divide the data into k clusters and then evaluate these clusters based on some criterion, and then they make some changes to the clusters. Okay. Again they evaluate, see whether there is an improvement or not. Right. So again it partitions the data into k clusters. Again it evaluates, see the improvement, and so forth. Right. So there would be some swapping as compared to the initial clusters. So initial clusters are randomly divided into k clusters. All the data points are randomly divided into k clusters, and then they evaluate the clusters based on some criteria, and then swap the points between the clusters, and then again evaluate. So this process is repeated for multiple times. In principle, optimal partition is achieved via minimizing the sum of square distance to its representative objects. Like it means that the distance between the centroid and the other points should be minimized for all the clusters. So this could be one of the criteria. We'll see one example that will be more clear to you. If it is not clear to you at the end of the example, then please let me know. So K-means clustering algorithm is example for this partitioning based clustering technique. Okay, so given the cluster number, it means K must be supplied as an input for this algorithm. How many number of clusters you want to make. Okay, so these are the steps. We are initializing set of seed points, that is randomly initializing the seed points. These seed points we also call them as the representative points of the clusters, or we also call them as the centroids. Right. Once we get the seed point, we assign each object to the cluster of the nearest seed point. Okay. So this nearest or farthest we measure using some distance metric. Okay, Euclidean distance or Manhattan distance. Like that, there are various distance metric based on the kind of data available at hand. Right. So using this, one of these distance measures, we measure the distance between the seed point and each and every object and assign the object to a nearest seed point, cluster of a nearest seed point. And then we compute the new seed point. It means we update the centroid because the clusters are changing now. We take the centroid as the seed point. Okay, and again we repeat the procedure, assign them to the nearest seed point and update the centroid. Okay, till there is no change in the clusters, we repeat this process. We'll see the example that will be more clear to you. If not, please let me know. So this is an example. We have got 4 kinds of medicine, A, B, C, D, and each one of these medicine is represented with 2 features, weight and pH index. Right? And our goal is to group these 4 medicine into 2 groups. So number of clusters is 2. So K equal to 2 in this example. And we have got 4 objects. Number of clusters that you want to make is 2. Right? So, and these are the data points that you can visualize, right side figure, A, B, C, D. Right? So what is the first step? Initialization of the seed points or the centroids. So you take these seed points randomly. Let's say when I randomly pick, seed points are A and B. Okay, when I'm randomly picking, let's say the seed points are got seed points as A and B, right? So these are the seed points indicated with stars, right? So the first step is done. Initialization is done. We have initialized the seed points randomly. What is the next step? Compute the distance from each object to the seed point. Okay, compute the distance from A2 for seed point 1, B to seed point 1, C to seed point 1, D to seed point 1, and similarly compute the distance from each object to seed point 2. Okay, so this is the summary of the distance at this iteration 0. Okay, so these are the seed point 1, seed point 2. This is A, B, C, D. Okay, distance from seed point 1 to A is 0 because the seed point 1 and A are same. Distance from seed point 2 to A is 1. Okay, and this is how we have computed the distance using the Euclidean distance. Suppose if I want to measure the distance from D to centroid 1 or seed point 1 from here to here. Okay, so the distance is 5 minus 1 whole square plus 4 minus 1 whole square root of that, which is equivalent to 5, which is this. Okay, so what is 5? 5 is D. 5 minus 1, 4 minus 1. Right? So square root of 5 minus 1 whole square plus 4 minus 1 whole square, which is 5. Okay. Similarly, you can compute the distance from this to this, this to this. Right? So that you will get 4.24. Alright, so this is how you can measure the distance. So once you measure the distances are summarized here. Okay, so this is A, B, C, D, and this is seed point 1, seed point 2. So to which seed point A is closer, seed point 1 or seed point 2, according to these distances?
8.2.
Seed point 2, seed point 1, seed point 1, right? Because the distance is lesser as compared to the seed point 1 distance, right? So this is the distance between A and C1, which is 0, which is the distance between A and C2, which is 1. So because this distance is lesser, so C1 is closer. So we assign this A to C1, cluster 1. Okay, so we've got A in cluster 1. Now let's take another point, D. Okay. So to which cluster it is more closer, C1 or C2?
C2.
C2, right? So we assign this B to C2. Okay, next, DC, to which cluster it is closer, C1 or C2? C1 or C2, which is lesser? C2, right? Right? You assign C also to C2. And next, D is more closer to C2, right? So now, according to this, A is belongs to C1 and B, C, D are belong to C2, right? So this is one cluster and this is another cluster. Now we will update the seed points as the centroid. Okay, take the centroid of these individual points and update that as a seed point. So because we have got only one point in the centroid, in the cluster 1, centroid will not change. Centroid is equivalent to that point. We've got 3 points in cluster 2, and we take the average on each and every axis, then the resultant would be the centroid. So this would be the representative point now, or the seed point. Okay, now if you see, the seed points are changing now. Seed points and the representative points have changed now, right? So now, according to this new seed points, like, repeat the procedure.
Again.
Again, any query?
Lima wait.
Right. So according to this new seed points, again compute the distance. Distance from each and every object to the seed points. Right? So so these are the distances. Seed point, A, B, C, D, and this is C1 and C2. According to this distance measure, A is close to centroid 1 or centroid 2?
C1.
C1. So C1 is more closer to A. So we assign that to cluster 1. And according to this distance measure, B is closer to C1 or C2?
C1.
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 This also to C1. According to the distance measure, C is closer to C2. Right? So you assign this to cluster
D is
2.
also close to C2.
B is also closer to C2. You assign this to D. So clusters are updating now. If you see, they have been updated. So earlier it is only one point in cluster 1. Now it is changed. Okay, so there is a change in the cluster allotment. Okay, so update the seed points now again. Compute the centroids. So if you compute the centroids, and in this cluster, this is the centroid. In this cluster, this is the centroid. The centroids are changing now. So again, repeat the process with respect to the new centroids. Compute the distance from each and every object to the new centroid. Okay, so these are the distances. So according to this, can you cluster them into two groups? To which point, to which cluster A should belong to? C1 or C2?
C1.
This is more closer, it should belong to C1. And B must be belonging to
C1.
C1.
C1. C?
C2.
C2.
C2, C2.
C2, C2. Okay, is there any change in the clusters
No.
from the previous iteration to this? So
No.
there is no change in the cluster. So even if you repeat the procedure for number of times, there will not be any change in the cluster. So stop because there is no new assignment of membership in each clusters. So there is no longer change. You stop it here. So this is what the partition based algorithms are doing. They're starting with some clusters, evaluating them based on some criterion, updating the clusters, and again evaluating them based on some criterion, repeating the process for many number of times, and they stop when there is no change in the cluster allotment. Okay, so that is how they perform this updation, right? This is an example of partition-based clustering technique. So any query? Is that clear so far? Question from Srinivas. Irrespective of the initial clusters, do results the same, or it will change? It will change, Srinivas sir. So it is, we'll see that is the disadvantage of K-mean. It is sensitive to the initial seed points. Yeah. Right. So strengths of K-means are very simple. It is easy to understand and implement. It is efficient also. If you see the time complexity, it is just order of Tk, where n is the number of data points, k is the number of clusters, and t is the number of iterations. If the weakness, if you see, the algorithm is only applicable if the mean is defined. If the mean is not defined, then the algorithm is not applicable. And the user needs to specify k explicitly. So this is a parameter that the user needs to specify, and it requires some domain knowledge. And the algorithm is sensitive to outliers. Like, what are the outliers? Outliers are the data points that are very far away from the other data points, that are very different from the other data points. outliers could be due to errors in data recording or some special data points with very different values. Like maybe when you are recording some value, instead of entering 6, when you're recording height, instead of recording 6, you might have recorded 60 by mistake. So that will become an outlier, which will be very different from 60 feet person will be very different from the other, no? Or there will be some special person with height 10 feet. Okay, so that is also outlier. So outlier could be due to errors in data recording or some special data points with very different values. Right? So these are the weakness, and other weakness is that it is sensitive to the outliers. Right? For example, if this is the outlier, it tries to incorporate this outlier also into the cluster. So as a result, you will have clusters like this. This is one cluster, this is another cluster. Whereas this is an outlier, if you ignore this, you will find two natural groups of data points in the data set. That is, this is one, this is another one. Okay, these are the ideal clusters. This should be an outlier. Whereas this is, if you try to incorporate this outlier into the cluster, you will have a bad cluster, something like this you can see in the figure. Right. So what is to deal with outliers? One method is to remove some data points in the clustering process that are much farther away from the centroid than the other data points. So when you are iterating it over the number of iterating it over itself, you monitor the data points. If you find them to be very different from the others, remove them. Okay, so to be safe, you monitor them over a number of iterations. Okay, for few iterations you will monitor them. Even in after few number of iterations also, if you are finding it to be very different from the others, then you remove it. Okay, or another way is that perform a random sampling. Since sampling, we select very few small subset of the data points, very less chance of selecting outliers in that sample. Okay, and you assign the rest of the points based on this sample. This is another way to deal with outliers. Okay, so this point, sir, Srinivas sir, you have mentioned, the algorithm is sensitive to initial seed points. Right, for example, if I select the seed points as this is one seed point and this is another seed point. Okay, so in iteration 1 also it is this, in iteration 2 also it will be this. So the clusters will be like this. Whereas if I define the seed points like this one and this one, then the clusters will be like this. Okay, if I define the seed points and I randomly select if it is like this and like this, then the clusters will be like this. Okay, so it is sensitive to the initial seeds. There are many algorithms that wisely select these initial seed points. The extensions of K-means algorithm, there are various algorithms to wisely select the initial seed points so that it will not lead to the erroneous results. Okay, so please do explore if you are. So if we use different seeds, we may get good results, something like this. Right. Another weakness is that K-means algorithm is not suitable for discovering clusters with arbitrary shape. Okay, so it cannot discover the clusters with arbitrary shape. So clusters that are not hyperellipsoids. So it can only detect the clusters with hyperellipsoids or hyperspheres, something like this. But if you have clusters, what are the two natural group of clusters? This is one and this is another, right? But the K-means clustering algorithm doing clustering like this. Okay, so this is another weakness of the K-means clustering algorithm. Okay, so let us see how the upcoming clustering techniques avoid some of these problems. Okay, hierarchical clustering. So if you see the classification, first is partition-based clustering technique, in which we have seen the K-means clustering algorithm. The second category is hierarchical clustering. Okay, so in this we will see agglomerative clustering, right? So hierarchical clustering approach, it clusters, typical clustering analysis approach via partitioning the data set sequentially. So there is a natural hierarchical decomposition of the objects, and it is trying to identify that natural decomposition of the objects at different levels. Okay, so it constructs the nested partition layer by layer via grouping objects into tree-like structure, tree of clusters. And we use the distance matrix as a clustering criteria here. We'll see with example, then you'll get better understanding. And mainly, there are two types of hierarchical clustering approach. One is agglomerative and the other one is divisive. Both of them are sequential clustering strategies for constructing a tree of clusters. Okay. Am I going fast?
No, sir, it's fine.
Right. Okay. Thank you. Right. So, agglomerative is a bottom-up strategy. Divisive is a top-down strategy. In agglomerative, we initially start with each data object as a one cluster. Okay. So we're starting with each data object as a one cluster and then try to merge these atomic cluster into larger and larger groups. Okay, so this is bottom-up approach, starting with each data point as one cluster and gradually merging them, finally making them as a single cluster. Another one is divisive. It starts with all the data points as a single cluster and then subdivided into smaller and smaller clusters. Right. So let us see the illustration of this agglomerative approach, starting each data point as a one cluster and merge two clusters that are most similar to one another. Like maybe A and B are most similar to one another, you merge them. Now the clusters available are A, B, C, D, E. A, B, C, D, E. Four clusters we have, right? You merge the two most similar clusters again. Let's say D and E. Now we have got three clusters. AB one cluster, DE another cluster, C is another cluster. You merge the two most similar clusters again, like this, C, D, E. Now we've got two clusters, merge them into a single cluster. Okay, so this is agglomerative approach, starting with individual singleton elements as the cluster and then gradually merging them into larger and larger clusters. Divisive approach is the reverse of this. You start with every element in a single cluster like this, gradually split into two subclusters, dissimilar ones into subclusters, and then smaller and smaller clusters. You repeat this procedure till each cluster get only one element. Okay, this is a divisive approach. Okay, and dendrogram is a binary tree that shows how clusters are merged or split hierarchically. Okay, so each node in the tree is a cluster and each leaf node is a singleton cluster. So this represents how the clusters are merged at each and every time step. Okay, so for example, at this stage, these two are merged. At the later stage, these two are merged. At the later stage, this and this are merged. Like that, it is showing the hierarchical decomposition, hierarchy of how the clusters are merged or split. Okay, so suppose if this is a dendrogram, if I cut this dendrogram at this level, how many clusters will I have? Suppose if I cut the dendrogram at this level, how many clusters?
2.
Two clusters, right? This is one cluster and this is another cluster. Okay, so this is one cluster, this is another cluster. Suppose if I cut the dendrogram at the next level here, how many clusters?
3.
Three clusters, right? Three clusters. So depending on at what level you want to perform this clustering technique, you may have a different groups of clusters, different number of clusters also. Right. Now the question is how to merge the clusters. How to measure the distance between the clusters. We said we will merge the clusters that are similar to one another, most similar to one another. Right. It means that they are nearer to one another. Right. So how to measure that nearness or right? How to measure the distance between the clusters. So there are many ways to measure the distance between the clusters. Cluster means what? Cluster is a set of points. It's not a single element, right? So cluster has got more than one element, right? So if you want to measure the distance between the two clusters, you have to consider the individual points of both the clusters. Okay, in what way you consider and what are the points that you would consider? Based on that, we have got different methods to measure the distance between the clusters. Okay. So the distance between the clusters is usually defined on the basis of distance between the objects. So we have got different ways of measuring single link, complete link, average link and centroid based distance. So in case of single link, we take the distance as the closest pair of distance between the closest pair of the data objects. Okay, so the closest distance possible between the clusters is taken as the distance between the clusters. So this is single link agglomerative clustering. In case of complete link, we take the farthest distance, farthest pair of data objects we consider, and we take the distance between them as the distance between the clusters. This is complete link. Average link considers all the pairs of distances and take the average over them. This is average link. And the centroid based distance, any guess? Centroid distance?
Distance between centroids of two clusters.
Distance between the centroids of the individual clusters is taken as the distance between the clusters, like this, right? So depending on what points that you would consider, we have different agglomerative clustering techniques. Single link is minimum distance, complete link is the farthest distance, average link is the average distance, centroid is the centroid distance between the centroids, right? So let us see one of them. I mean, the example we'll see for all of them, but later we'll see one of these agglomerative clustering techniques. Okay, so suppose this is the these are the points. A, B, C, D are the points represented in a single dimension. A equal to 1, B equal to 2, C equal to 4, D equal to 5, E equal to 6. And let's suppose A and B belongs to cluster 1 and C, D, E belongs to another cluster. Okay, now I ask you to measure the distance between C1 and C2. Okay, so what would be this distance if I follow single link? What would be this distance if I follow complete link? What would be this distance if I follow average link? Right. So first of all, I measure the distance metric, distance from each and every object to each and every other object. So A to A to B, A to C, so on. So this is the distance metric. Okay, so if I take the single link, I take the distance between the all possible pairs. What are the all possible pairs? A and B are one cluster, C, D, E are another cluster. What are the possible pairs? AC, AD, AE and BC, PD, PC. Okay, compute the distance from A to C, A to D, A to E, B to C, B to D, B to E, and take minimum of them as the distance between the centroids. Okay, so A to C is 3, so this is 3. A to D is 4, this is 4. Like that, you take all the possible pair distances and minimum of them is the distance in case of single link. In case of complete link, maximum distance. So among this 3, 4, 5, 2, 4, 5 is the maximum, you take maximum. In case of average link, take all the distances, average as the final distance. So this is how you can measure the distance between the centroids using different measures. Okay, so to summarize the agglomerative algorithm, we're converting all object features into distance metric. We set each object as a cluster and we repeat the process until convergence. We merge two closest clusters and update the distance metrics. So this is what we are doing. So let us see with example, then it will, you will understand it better. So these are the data points. I've got 6 points, A, B, C, D, E, F. So these are the 6 data points. And each data point is expressed in a two-dimensional space, x1 and x2. And distance, we can use the Euclidean distance to compute the distance point between the data points. And this is the distance matrix. Right. So I've computed the distance metric. Initially, each and every data point is a separate cluster. So I'm computing the distance from each and every cluster to each and every other cluster. So this is the distance metric and it is symmetric. Okay. So the values between distance between A to B and B to A are same. You can see that 0.71, 0.71. Okay. So among these entries, which is the lowest value? 0.5 is the lowest value, and it is the distance between D and F. What does it mean? It means that D and F are the closest clusters, right? Very similar clusters. So what is the next step? We have to merge them together. So D and F should be made as one cluster, right? So D and F is the closest cluster. So merge them into a single cluster. Now the cluster information is updated. Now the available clusters are 5. A is one cluster, B is another cluster, C is another cluster, D and F together one cluster, and E is another cluster. So what are the values that would change? We have to compute the distance from the new cluster to the other clusters. Rest of them will be same. These entries will not change, right? Only with respect to the new clusters, the entries will change. So we have to update these entries, right? So from this new cluster to each and every other cluster, we have to find out the distance. So we compute the distance. We take single link agglomerative clustering here. So we take minimum distance. So according to that, we update the entries. So these are the new values that we have got, and this is the updated distance matrix. So which one is the minimum value among all these entries? Which one is the minimum value among all these entries?
0.7.
0.71 is the minimum value, which is in between A and B. So what is the next step that we have to do here? We have to
A and
merge
B.
A
A and B.
B, right? So merge A and B into a single cluster, right? So this is the updated cluster information. AB one cluster, DF another cluster, C is another cluster, E is another cluster. So we have got 4 clusters now. The distance matrix will be of size 4 by 4, right? And these are the entries that will change. The AB is the new cluster. So according to this new cluster, we have to compute the distance to the other clusters. So update them again using the same procedure. Okay, single link procedure. You update the distance matrix, and this is the updated distance matrix. Among the entries, one is the minimum, right? And it is between E and DF, right? So it is between E and DF, right? So what is the next step? If you identify the minimum distance, what is the next step? Merge them, right? Which 2 clusters do we have to merge?
And DF.
E and DF, right? So we merged them. So we have merged them, and the updated cluster information is this. AB one cluster, C is another cluster, E, D, F together one cluster, right? And update the distance metric. This 1.41 is the minimum value, which is in between C and E, D, F. Close them together like this, and you will get the updated distance matrix as this, and merge them. Finally, you will get this as a single cluster. So if you see the dendrogram for this, we have merged D and F first, then A and B later, then we have merged E, D, F next, C, E, D, F next, and then finally we have merged A, B with C, D, E, F. Okay, so this is the dendrogram representation of this clustering process that we have done. Okay. So depending on where you cut this dendrogram, you may have a different groups of different clusters, right? Now the question is, we have got different distance measures: single link, complete link, average link, centroid basin distance. We have got different distance measure to measure the distance between the clusters. So which distance measure is better? So each method has both the advantages and disadvantages, and which measure is best depends on the application. Single link and complete link are the most commonly used methods. So if you see the single link, it can find irregular shaped clusters, and it is sensitive to the outliers. And it also suffers from chaining effect. Even if one of the point is connected, then it will make that as a cluster. Right. So complete link, average link, or the centroid based distance, they're more robust to the outliers as compared to the single link. But the problem is they tend to break large clusters into single clusters. I mean, small clusters. And they prefer spherical clusters. They couldn't identify the clusters with arbitrary shape. Okay, so that's the disadvantage with this. Okay, so then, I mean, you need not specify K in this case, right? And most of them are not robust, they're not sensitive to the outliers, they're not sensitive to the initial seeds, right? All these are the advantages of the hierarchical clustering as compared to the K-means clustering. But the problem here is that most of these algorithms couldn't identify the clusters of arbitrary shape. Okay, so let us see whether the coming algorithm address that problem or not. Is it clear so far? Am I going fast?
Yes. So fine.
Sir,
Yes,
it is
sir.
clear.
Okay.
It's okay, sir.
Yeah, I need not reduce the speed, no? Should I reduce?
Sir,
Pace.
Not
fine.
necessary.
Not necessary.
It's fine. Okay, cool.
Right. So, one doubt, sir, actually.
Yeah.
So, so far, what we have seen is that, especially in K means, we are reducing the intra-cluster distance, but the principle of clustering says that we have to also maximize the inter-cluster distance. But is it intuitive that if we reduce the intra-cluster distance, the inter-cluster distance automatically maximizes? If such is if such intuition is inbuilt, then why to specify it in the principle of clustering? I mean, we are focusing only on minimizing the intra cluster distance. We are not explicitly focusing on maximizing inter-cluster distance. So
That is the
intuitive.
objective of K-means clustering, but not necessarily the objective of every clustering technique.
Okay. Even in K-means clustering, we are
So
only
suppose you see LDA you have already computed, no?
yes, sir.
LDA, if you see LDA, what are you doing there? When you are projecting in the projected space, you want this inter-cluster distance to be maximized and intra-cluster distance to be minimized, isn't it? Because
Yes.
you're giving the one in the numerator, the other one in the denominator. Both the objectives you are specifying there.
Yes.
Okay, so the assumptions may vary from algorithm to algorithm.
Okay. So finally, in clustering in prediction time, we need to compute the distance between the unlabeled point, I mean unknown point to each and every cluster center. Is that the only way out?
To predict to which cluster this point belong to.
Yes, sir.
Yeah, we compute the distance, we assign it to the closest.
Okay. That is the only way for all clustering algorithms.
Yeah.
Yes. Thank you, sir. Thank you, sir.
Yeah, right. Is there any question? Yeah. Srinivas said. In the same case as classification. Yes, sir. We can apply. We'll see one of the example also. Digit classification. If we complete it. Okay. At least we'll demonstrate the clustering, even if we don't complete everything. All right. Then a density-based clustering approach. Okay, so if you see this example slide set, all these are the points that are densely connected. All these are the points that are densely connected to each other, isn't it? And these are the points that are densely connected to each other. So now you might have got understanding that what I mean by densely connected to each other, isn't it? So the gap between the points is less. So if you see this point and this point, there is some gap between them. They're not densely connected to each other. Whereas if you see these set of points, they're densely connected to one another. These set of points, they're densely connected to one another. Right? So these set of points are densely connected to one another. Alright. So clustering is based on the local connectivity and density functions. In the case of density-based clustering methods. So the basic idea here is clusters are the dense regions in the data space. and they are separated by regions of lower object density. Okay, and cluster is defined as the maximum set of densely connected points. Okay, so each cluster has a considerably higher density of points than the outside of the cluster. So this is what the assumption in case of density-based clustering methods. So if you consider the major features of these density-based clusters, they can discover the clusters of arbitrary shape. Whereas the partition K-means clustering algorithm or this agglomerative-based clustering algorithm couldn't do that. And it handles noisy or outlier points automatically. And it only requires one scan. If you see this, the previous two methods, they're scanning the database multiple times. In each and every iteration, they're scanning the database. Whereas in case of DBSCAN, density-based clustering algorithm, only one scan is required. Why is this important? If you are scanning the data for multiple times, the time complexity would increase. So every time you may not bring the whole data set into the primary memory, main memory, right? So therefore, you may be switching in between the main memory to the disk, right? So therefore, if you go for the multiple scans, this transfer from main memory to the disk to the main memory, that is also a costly operation, right? So therefore, the complexity or time required to execute the algorithm will increase if you go for the multiple scans. So that requirement is not there in case of density-based clustering methods because it is a single scan algorithm. One scan only required. So these are the major features of density-based clustering methods. So in this density-based spatial clustering algorithm, we call it as a DBSCAN algorithm. There are two global parameters. It is a kind of density-based clustering method. It comes under that category. In this, two parameters are required. One is epsilon and other one is the minimum points. Epsilon defines the maximum radius of the neighborhood. Within what neighborhood we have to explore this, right? So that radius is defined using epsilon. And minimum points is the minimum number of points in an epsilon neighborhood of that point. Okay, suppose if you see this point, what are the, within this neighborhood, how many points are there? 3 points are there. Similarly, if you see this point, within this neighborhood, how many points are there? 7 points are there. Similarly, if you see this point, within this epsilon neighborhood, how many points are there? 4 points are there. Right? 3 points probably. Right? So like that, you define the minimum number of points within the epsilon neighborhood. And density is the number of points within that specified radius. So we define the density as the number of points within that radius. Okay. And these are the some of the definitions that we're going to use in the algorithm. So please be little careful in understanding this. Core point, noisy point, border point. 3 different definitions I am giving now. We say that a point is a core point if it has got more than specified number of points within the epsilon neighborhood. Okay, so if the minimum number of points that I specify is 4, within this epsilon neighborhood, I've got 6 points with me, which is greater than 4, right? 6 is greater than 4. Correct? So it means that within the epsilon neighborhood, I've got more than specified number of points, more than minimum number of points. Then I can declare this as a core point. Okay, so this is a core point. This is an example of core point. A border point has got less than minimum number of points, but it is a border. It is in the neighborhood of another core point. Suppose if you see this. So within this epsilon neighborhood, it has got only 3 points. 3 points, which is less than 4. But it is in the neighborhood of another core point. So we call this as a border point. The point itself is not a core point, but it is in the epsilon neighborhood of another core point. That kind of point we call it as a border point. Okay, and the point which is neither a core point nor a border point, we call that as a noisy point. So for example, if you see this, within this neighborhood we have got less than 4 number of points. So therefore it is not a core point. Is it in the border or is it in the epsilon neighborhood of any other point? Is it in the epsilon neighborhood of any other point? No. So therefore, it is not a core point, not a border point. Therefore, it is a noisy point. Okay. So have you understood the difference between all these 3 points? Core point, border point, and noisy point. Is that clear?
Yes, noisy point need not be outlier, sir.
Noisy point usually outliers are noise. Some noise are outlier.
Uh, Here, I mean, there is no constraint. So if some point is noisy, the region beyond that noisy point, we cannot generalize whether they are noise or not, because there are points above the noisy point which may or may not be noise.
Point above the noisy point means
So in this example, we have noisy
two points.
yeah,
You cannot generalize because there may be some point here, and
yes.
this may be within that border of it.
Yeah, yes, fine. So it is only specific to
Yeah.
noise point. Yeah. Yes, thank you, sir.
So now we again define another notation, density reachability. Whether one point is within the density reachability of the another point or not. We say that object Q is directly density reachable from object P if P is a core point and Q is in P's epsilon neighborhood. Okay, so I repeat, object Q is density reachable from P. So this is P. We say that Q is reachable from P. Q is reachable from P. Okay, so when we say that if P is a core point and Q is within the epsilon neighborhood of this P. If it is so, we say that Q is density reachable from P. Okay, and this density reachability is asymmetric. You cannot say that if P is Q is density reachable from P, P is density reachable from Q. You cannot say this. Okay, it is asymmetric, right? So this is density reachability. So according to this, is Q density reachable from P? In this example, what are the constraints? P
Yes,
should be a core point. Yes, P is a core
Yes,
point.
sir.
And Q
Yes.
is within the epsilon neighborhood of P. So
yes.
therefore, it is density reachable from P. Another question, is Q density reachable from P? Sorry,
Not
P density reachable from Q?
No.
no, sir.
No.
Q is
Why?
not a core point.
Because Q is not a core point, right?
Yes.
Right. So density reachability can be direct or it can be indirect. Okay. So there may be intermediate points, like for example, in this case, P is density reachable from Q. Okay, but it is not directly. There are some intermediate points. P1 is directly density reachable from Q. P2 is directly density reachable from P1, and P is directly density reachable from P2. There is a chain of density reachability here, and this chain of density reachability forming indirect density reachability. So P is indirectly density reachable from Q, but not directly. Okay, so in this case, as you can see here. So similar is the here, the vice versa may not be true. So P is density reachable from Q, but Q may not be a density reachable from P. Then we define density connectivity. Okay, so if 2 points P and Q are density reachable from a common point O, then we say that P and Q are densely connected to each other. Right? So density connectivity is symmetric. If P is densely connected to Q, Q is also densely connected to P. Right? I repeat the whole thing. If 2 points P and Q are density reachable from a common point O, then we say that P and Q are densely connected to each other. And if P is densely connected to Q, Q is also densely connected to P. This is symmetric relation, right? So now what is our algorithm? Right. Oh, sorry. Oh, going back. So right. So this is our algorithm. What is a cluster? Given a data set T, parameters epsilon and minimum points, a cluster C is a subset of T satisfying the following constraints. For all the points that belong to one cluster, they must be density reachable from one another. Okay, P and Q belong to cluster. P must be density reachable from Q. Okay, so Q is density reachable from P with respect to epsilon and minimum points. Then Q can say that Q is belongs to C. So your point P is belongs to cluster. You can also say Q is belongs to cluster if this condition is satisfied. If there is a density reachability from P to Q, right? And for all the data points, P and Q belongs to C. P is densely connected to Q with respect to epsilon and minimum points. Then also you can include both of them in the cluster C. Okay, so either if it is density reachable or densely connected, you include that point. So that is the very simple way of saying this. Okay, right? So if P belongs to C and you include Q also in the C, if Q is density reachable from P or densely connected to P, then in both the cases you will include that in the cluster. Okay, so note that cluster contains core points as well as the border points, but not the noisy points. So this is the algorithm. You are starting with some seed point, some starting point, and exploring the neighborhood of that. So this is the neighborhood of that. So you are exploring the neighborhood of those green points also, green points also, again green points also, right? So when there is no other point to explore within that neighborhood, you stop and again randomly initialize with another point. Okay, so you're making this all these points as a single cluster, starting with another point. So within this epsilon neighborhood, there is no point. So you declare this as a noisy or outlier point. Right. Again, you start with another point, explore the neighborhood of that, neighborhood of those points, neighborhood of those points, and finally make them as a single cluster. Right. So when you are exploring these points, you will only consider the core points and the border points. So you will start exploring the neighborhood of the core points or the border points, right? But not the noisy points. Right. So this is another example. You're starting with red color point, exploring the neighborhood of that, and making them a different color, and exploring the neighborhood of the those points with the sky blue color, and assigning the sky blue color to them also. So whenever you are exploring a particular point, you're making that red, right? And exploring the neighborhood of those points. Finally, you're making them as a single cluster, right? So that is the procedure. Okay, so when this DB-scan algorithm doesn't work well, is that it cannot handle the varying densities. Like for example, if you see the varying densities, the highly dense here, low dense here. Okay, so it cannot handle the clusters with varying densities. And it is also sensitive to the parameters. With the different parameters, if you give different values to this epsilon and minimum number of points, you may get different kinds of clustering. Like for the example, this. If these are the clusters with different values of epsilon and minimum number of points, you may get different kinds of clusters as you can see in these figures. Right? So it is sensitive to parameters and it is difficult to determine these parameters. So the advantage is that clusters can have arbitrary shape and size, and the number of clusters is determined automatically. You need not pass the number of clusters as the input parameter, and it can separate the clusters from surrounding noise. So it is not sensitive to the outliers. Disadvantage is that input parameters may be difficult to determine, and in some situations, very sensitive to input parameter setting. Right? That's all. Happy learning. Thank you very much. So let me go through the code if you have any queries. Any queries?
Sir,
Yeah.
in density clustering, you told that borders are also considered, sir, border points.
Where, yeah, border points also considered to include in
So,
the cluster. We
so
consider
won't
the
few elements be repeated in two clusters?
uh-huh. Sorry, repeat it.
Few elements may be mixed in two clusters.
No. You are exploring the neighborhood of that. When you don't find any neighborhood, then only you stop. Otherwise, you make all of them as a single cluster.
Okay.
Did you get my point? You're starting with a single point, exploring the neighborhood of those, all like in a iterative fashion. And whenever you don't find any point within that neighborhood of all these points, then you will stop, make that as a cluster, and you will start with another point. Okay.
Okay, sir.
Yeah. Any other query? Right. Okay. Could you see my screen? Clustering demo?
Yes, sir.
Right. So these are the different libraries that I require. I've imported them and I'm creating a data set for this. I'm importing that also from sklearn. From sklearn.datasets.samples generator, I'm importing make blobs to create a blobs kind of data like this, right? With 4 centers, I'm creating 300 samples. So the inputs that I am passing for this are number of samples, centroids, and cluster standard deviation. If you give more standard deviation, there could be more variance in the clusters. If you give less value, then less variance, right? And I'm just plotting it for you, scattering, just to show you that how it looks like. So this is how the data is looking like. So there are 4 natural clusters in the data. Right. Let us apply k-means clustering algorithm and see whether this k-means clustering algorithm could identify these 4 natural groups of clusters or not. Right. So I've called this from sklearn.cluster. I'm importing k-means clustering algorithm and I'm passing the number of clusters as 4. Okay. So once I get the model, I'm fitting the model to the data. So x is to x I'm fitting and I'm predicting for x again. Okay. So once I predict for x and scatter them based on and plot them based on their cluster. Okay, so I'm passing cluster number cluster value to assign a color to it, and this is the size. Size is 50, and color map I take where this, right? So you can see this, right? And I've also plotted the centroids. So centers you can get it by accessing this object k means dot clusters underscore centers underscore. So you would get the centers. So I've plotted the centers also with size 200 to appear big. So these are the centers, the big balls are the centroids. And these are the individual points, each color represents one cluster. So you can see that k-means clustering algorithm could identify these clusters perfectly, right? So let us see another data set see whether the k-means clustering algorithm could identify the clusters with arbitrary shape or not. Okay, so for that I'm making moons kind of data like this, like this. Okay, so I just made moons kind of data and I called make moons for that. Number of points that I've generated is 200 and noise with noise of 0.05. Okay, so if I plot this data, this is one cluster and this is another cluster. If you don't assign any color to it, you can see that, right? The upper moon is one cluster, lower moon is another cluster. But if I apply k-means clustering algorithm, and this is the how it is identifying the cluster. all the purple colored points, it is identifying as one cluster, and all the yellow colored points, it is identifying as another cluster. Right? So isn't it, I mean, sensitive to these arbitrary shapes? It couldn't identify the arbitrary shapes, right? It is clear from this example, isn't it? Right. So let us see whether the DB-scan algorithm identify the clusters of arbitrary shape or not. So we imported the DB-scan algorithm again from sklearn.clusters, and I have passed these parameters required by the clustering algorithm, epsilon and minimum number of samples. Epsilon I give 0.3, minimum samples 10. You can also use fit predict directly instead of calling fit first and predict next. You can directly call fit predict on the X. So this is usually we do when you want to fit and predict for the same data. Right? Fit predict you can directly call. Even in case of k-means you can directly call fit predict. Right? It is returning the labels. Labels are the cluster numbers to which they belong to. And I'm scattering them and assigning colors based on the labels. So if you see this, all the purple colored points belong to one cluster and all the yellow colored points belong to another cluster. By the way, this uh, files I've already shared with you in Drive. So if you want to execute them, you can execute. Right. So you can see that it could identify the clusters with arbitrary shape. Right. So isn't it identifying the clusters with arbitrary shape? DB-scan technique? It is identifying, right? Yes. Good. Then K means on digits data. So how do you classify the digits? Okay. So this is one of the participants has asked this, right? So for this, I'm importing dataset, real-time dataset from sklearn.datasets. I'm importing load digits. So this load digits is the image data, right? So given the handwritten digit, okay, I am importing these digits and loading the digits, and shape of the digits, if you see, 1797 by 64. 1797 is the number of instances, 64 are the number of features. So each one of this image is of size 8 by 8, 8 by 8, and if you consider all the pixels of this 8 by 8, you will get 64. Okay, right? So 64 features we have got, and we are finding, calling k-means clustering with the number of clusters as 10. So number of clusters is 10 because we have got 10 digits, 0 to 9, right? Then we are fit predicting digits dot data, it will returns you the clusters. Okay, so if you see the cluster center shape, it is of size 10 by 64. So 10 clusters, 10 centroids, and number of which is 64. Okay, so now I'm just plotting the centroids of this for you and reshaping them to 8 by 8 centroids, because 64 I'm reshaping them to 8 by 8. You can see this, right? This first one centroid is close to 4, the second centroid is close to 3, third centroid is close to 1, and so forth. Like this we have got the centroids. Now when we are assigning clusters, when we are assigning labels, look at the original data and among the clusters which is more repeated. Okay, so for example, if more number of data points belong to digit 2, more number of members in the cluster belong to cluster 2, you assign all the data points belong to that cluster as a digit 2. So like that, you assign the class labels. So this is the code for that. So maximum number of repetitions, the mode we are doing for this, mode is the maximum repeated digit we are assigning, right? And then I'm just using this heat map, which is from Seaborn, right, to indicate that how the classification or misclassification errors. You can see this, that here 99 of 8s are classified as 1s, right? Again here 42 of 9s are classified as 6, and 48 of class 9 are classified as class 8. So this is a confusion metric. Okay, right? Um, right, and again here another 24 number of 2s are classified as 1s. Okay, right? So this is a misclassification error, and this is for digit classification. Another application of this is color compression or image compression. So instead of representing the image with so many number of colors, you can represent the image with limited number of colors. This we call it as a color compression. So for this, I've loaded sample image, and I loaded this china.jpg, and this is how it is looking like. I've shown this to you using imshow China. So this is how the image is looking like. Okay, and I'm just normalizing this data by dividing it with 255 because I want to bring all the data entries in the similar range. So I've normalized it and bring them to 0 to 1 scale. Okay, so once I do this, this is of size 427 by 640 by 3, where 3 is the number of channels, red, green, blue channels. Okay, I'm reshaping it to a single dimension. I mean, each channel in one dimension. So I'm reshaping them to 427 by 640. It means this many number of features I'm taking 2,73,280. So once I reshape them, I perform clustering technique on the colors. Okay. So each data entry I have some intensity value. I perform clustering technique on that. Right. So I apply k-means of 16 and I fit on the data. So this is the data that I have, and I'm just fitting this data and applying k-means clustering algorithm. Now I access the cluster centroids, clusters and underscore centers underscore, right? And now what am I doing? I am replacing this data with its centroid. So each point is replaced with centroid value. I'm predicting the data to which cluster it belongs to. Suppose if it says 2, it belongs to. I'm taking the cluster center of 2 and taking that as a new color. So the original color is replaced with its centroid. Did you get my point? So for each entry, I am predicting to which cluster it belongs to. And suppose if it says 2 or 3, the corresponding cluster I am taking as the new color. So like this, I got all the new color for each and every pixel value, right? So new colors, I'm reshaping them and like a China dot shape. So I'm reshaping them with the same size as the China dot shape. Okay, so if I plot this, this is the original image and this is the 16 color image. So not much information loss. You can see that. So this is the original image. This is the 16 color image. So you're compressing this image and representing the image with only 16 colors. This is how you can use clustering technique for color compression. Right? Any query? I'll take, otherwise we'll wind up. No query? Thank you. Then, good night.
Good night, sir.
Thank you, sir. Actually, it's not a query related.